Checking 1, 2. Check, check. Good morning. Checking 1, 2. Check, check. Unless it's not our room. Check, check. Checking 1, 2. Can you hear it? You hear it? Good morning, Roseville. You need more? Alrighty. How about now? Better? Alrighty. Checking 1, 2. We all good? Both things. You're gonna have to be my ears in this operation. Hello. Alrighty. I'm just checking for feedback. Over here. I don't hear anything. I think we're good. Alrighty. Yep. my coworker was just like, he's seeing that everyone's sort of looking at me. So I guess we're not supposed to take the 3 seconds out. Yeah, they have like set they have time to do that. But that doesn't mean that some people don't take it anymore. Because it's just that.
That's an option. And then if I get to this here, the last two. It's like just remember if you want to see them. Okay. All right.
Sorry, I heard feedback. It's not, I don't think it's us. This is my boss. Yeah.
Yeah, good.
Yeah. I was, I cracked a bunch of joints in here, and
Me being old.
I did because you were talking about your shoulder, and I was like, my shoulder too, your elbow.
Like yesterday, I was on something like, yeah, you know, I just did this, and my elbow
You gotta see what you can do for that. I'll ask my mom. She's got arthritis, and well, if there's anything to help.
I was like, this hurts so bad.
Yeah.
26.
22.
When do we stop being young? 30?
Just a little. So you got time. When you hit 30, it's just like grandma would be in. Like, that's the first thing. When you hit 40, it's like, cool. Like, I just was talking on the phone and I was just, and my knee was like, oh.
Well, I said I had time in like 2013, and now 10 years later.
Look, enjoy it. Still wish I was back in 20.
Oh, I have a question though. Did you hear that feedback I sent you a video ago?
I did. We were downstairs.
Okay. I'm like 95% sure it wasn't making a video, but yeah.
But I don't want to be
Yeah. Oh my God. Don't do it. Don't do it. You're going to make magic. Look. I could copy him there. You're 9 a.m. You're 9 a.m.
9 a.m.
Is it 9? It's 9. You're 9 a.m.
You mean a meeting? Oh, no, it was meeting with, meeting with, all right, let me know if you're on. But you should feel important.
I should be on 45 for you to stay here.
Look where you
Oh.
I saved it to
You
the
didn't,
top. I
you
pinged
didn't,
it to the top.
you didn't press it though. You didn't press my message.
I be forgetting all of them. But I know
It's not-
it's you.
yeah. So I know the number.
All right.
Not really. One night of yes, but yeah. So this is for.
The only thing I think we really want to preserve. And this is what we're going to see.
No, it's the only one that doesn't have the the attachment. Great. Nicola also is not around. Is Nicola around? No, yeah, it's one of the two that haven't posted the slides yet. Huh? No, yeah, that's what that's where I checked. And I don't see him around as well. So plan B is to start with multi KVM. Or with Picker on FS, it's the same. Depends if we want to switch with the closest one or the one that has the same size. So. Did Michael arrive? No? Come on. You have to present from here. Okay. So, no, you have to use this one, yes.
Yep.
Because this is connected to Bluebot.
Videos to play to.
Yes.
The links are here. But...
Okay, yeah, you have internet, of course, yes. How do you do this? F5? Full screen, F9. Yeah, something like this.
Connect to the videos.
What?
The videos.
No, you had to come before. Now whatever it goes. So remember that you have 15 minutes.
Okay.
Now you have 30 minutes.
Yeah. So, hey everyone. My name is Michael Salon. I work for Microsoft. I'm a Linux kernel engineer, especially focused on security. And this talk is about leveraging KVM, virtualization for security. Madhavan should also be on the chat, so he should be able to answer questions, if any. Okay, so let's first start. Well, as you might know, Linux, and especially the kernel, is, complex. And there's, of course, vulnerabilities, and, well, we need to take that into account. So kernel integrity. So we define kernel integrity with a way to protect the kernel, in this case, guest VM kernel. So some data and also its code. So the idea is to make an attack to be, well, difficult or at least costly to change this data. Well, there's a lot of vulnerabilities, and some of them might be either exploited by user space or even through the network, the storage, or whatever. So the main trait here is, as I said, well, an attacker be able to change kernel memory, so the guest in this case, guest kernel memory. One thing to keep in mind is that, well, in this case, we trust the guest kernel at first because the guest wants to protect itself. But trust can diminish over time. So at first, thanks to mechanisms like secure boot, for instance, well, the guest trusts itself, but over time it might be it might open new interfaces and then get compromised. An extended strand model, so something to keep in mind, which would be interesting for future work, is well, for instance, using protected KVM. So initial PKVM, the idea is to make KVM more protected from the host, so from VMM, from QEMU, for instance. Conventional computing is something else, but the idea is, well, for VM to not trust, at least too much, or at least not at all, the hypervisor and then the VM. So here we want to use and to kind of improve the kernel self-protections. The issue with that is, well, it is a self-protection, so the kernel can be compromised, and then the attacker might be able to kind of disable these protections. So we like to rely on a higher privilege component, and in this case, the hypervisor KVM. There's a lot of stuff which are implemented either on the kernels or thanks to virtualizations. One of them, which is, I guess, one of the oldest one, is Windows virtualization-based security. But there are also the implementation for instance, for Android with Samsung RKP, but also on iPhone with AOS. So the main design here, what we like to be able to have, is for guest VM to configure themselves. Then for KVM to be able to manage and enforce, well, to enforce the guest wishes on itself, guest restrictions. And then for the VMM to be able to protect its resources, which is not you, and to be able to react to some attacks, for instance, to log them at least. From a usability point of view, well, we like this feature, security feature, to be easy to use. So we should not need users to configure themselves such security feature. But yeah, we like this to be, well, as simple as possible. And we should keep in mind that, well, users, anyone should be able to use their own kernels, and those need to be well-defined with a clean interface, and not to rely on existing, I mean, not only rely on hardware root of trusts. So to make it more flexible and to kind of delegate to the hypervisor the choice to use enforce this protection or not. So something to keep in mind, again, in a nutshell, chain of trust is something like this. When you boot a machine, well, you need to first trust the firmware, the bootloader, the host kernel, the VMM, and the hypervisor, and all that can be done with secure boot. So that is our initial trust. Then the hypervisor can launch VM. So in this case, most importantly, the guest kernel. And so the hypervisor can check and verify the authenticity of this guest kernel. So it might pertain to a customer. And then one of the goals of this kernel is to, well, make user space secure, and that might include authenticate user space applications. But it is the realm of the guest kernel, not the hypervisor. Here we're focusing on the hypervisor. trying to protect the guest kernel. There is two set of security policies we implemented. The first one is to use CPU registers pinning. It is mostly to restrict the use of control registers, which might be used to configure a kernel. For instance, to enforce or not write protections, smash map, and this kind of security features. Another important things to be able to enforce is protections on the guest kernel memory. So be able to enforce read-only or even non-executable kernel permissions on the kernel memory. So in a nutshell, so how does it work when you want to use a virtual machine? So the VMM is in charge to assigning a set of memory pages to the new virtual machine, then launch the VM, and then handle some VM exits, which might be part of the emulation process for devices. From a virtual machine point of view, like any kernel, it first starts, creates some memory mapping, sets some permission to them. And one thing which is so interesting about Linux is that it can, at the end of the boot process, to be able to also enforce another set of permissions, of restrictions on its own kernel memory. So that is, in practice, what you can find with init, reloaded data variables. And at runtime, the kernel can also change its own memory, of course, and especially to be able to add new executable mappings. So that might be the case for kernel module loadings, but also for eBPF JITs, for instance, or even F2A escape ropes that might change the kernel memory. So we sent first RFC a few months ago and another one a few days ago. So the main changes between these two are first, initially we only implemented protection for static kernel memories, so only based on kernel sections, which are kind of defined at boot time thanks to kernel symbols. Now we implemented a way to track the memory permissions at runtime and be able to kind of reflect these permissions to the IPSR. For now, there's no more execute the write security policies, which we'll get back later. But we first need to be okay with the mechanism we implemented. We leverage a new patch series, which is the pair page attribute patch series, which is kind of filling the gap of the move KVM feature, which was to track some guest pages. And also, we added a new KVM interface for the VMM to be aware of the request or the dial that the guest might do. And also, a way for the guest to know which features might be supported, are supported by the IPSO. So let's see about the KVM implementation. There's a first hypercall called log_here update, which takes 3 arguments. First one is a control register ID. Second one is bit flag or of masked, pinned flags. For instance, in this case, a white protection bit, and optional flags item. So there's two kind of VM exits which are implemented. The first one is, that can be enabled by the VMM, is when the guests ask KVM to enforce such restriction. And the second one is when the guests try to bypass this initial security policy. And in this case, it will get general protection fault. So bit of explanation about memory permissions. With virtualization, we have the ability to enforce a complementary layer of permissions. So on top of the permission that the guest can enforce on itself. So this is thanks to what we call Intel's EPT, or second layer authentication, or even two-dimensional paging. So that is the main feature we're using. And yeah, it is very important to keep in mind that it is a complementary layer of permissions. So it applies on top of existing kernel permissions. And only the hypervisor can change that.
Sorry, theoretically, time is up for your presentation, so I suggest that you switch to basically what should be the topic of the discussion, which will be the next 20 minutes, and so that we can actually start the discussion.
Yeah, so the idea was to present that for 30 minutes and then up.
No.
So
Say this wrap up the presentation part to move on to discussions. We have as much.
okay.
Feel free to just skip over stuff that you think people in KVM already know.
Okay.
And you can, like, when we discuss, you can show the slides.
Okay. So yeah, anyway, the slides will be online. Well, they are online, and there's also some demos, some videos, so you can watch them later. So yeah, in a nutshell, this specific hypercall to protect for the guest to request protections on memory pages. So there's also the embed computation, which is to be able to enforce executable memory to be able to split between kernel mode execution and use-based mode execution for efficient enforcement. So yeah, the idea is to also bring a new API for guests to implement that. So either for, well, if they're using KVM or either for using other hypervisor, for instance, Hyper-V. But yeah, the idea is to share a common goal and also share a test suite and so on. For this, we implemented memory page table data type, which is a new one, to especially deal with dynamic kernel memory permission management, to be able to track all the kernel mappings. And
So, I checked when you got acceptance. It said that it was 40 minutes total, of which 10 minutes can be presentation. We were told this 2 months ago. At this point, I think the problem with the HAKI is mostly about how to do the guest side engagement. So, what are the questions that you want from the audience? This is not a conference when you give a demo. If you wanted to give a demo, you had to come to another conference. Like, this should be clear. Like, I don't know what to say.
okay, so well, the main limitations are these ones.
I don't want to know the limitations. I want to know what questions you want from the audience.
Okay. So, well, there's some questions you have. For instance, every kernel modifications that are not related, for instance, to kernel module loading, for instance, using ftrace or kproops, well, we'd like to be able to know if this kind of change are legitimate or not. And that is, well, something we're not sure how to implement yet. And yeah, the question is, how can we move these patches forward? And yeah, to implement the first step. So the idea would be to first focus on the CR peeling patches. But yeah, there might be other ideas. And yeah, for general review, you'll see tomorrow more general talk on the refit track. And thank you. So, any question?
Yeah, so since this is the occasion where we have people that are not from the KVM community, do you have some quick explanation about how the guest side works? Because the problem is the host side work in KVM is stuff that a lot of people are, from the KVM community have seen and reviewed, and it's not particularly controversial. I think the more important and more complicated part is the guest side, where you have issues like you were saying before, where write and execute is hard to apply in Linux because there's a lot more patching going on than other kernels, such as Windows. Like when you apply a kprobe, for example, there may be other functions running in the same page, and the kprobe works by putting a breakpoint on the instruction, but you cannot really enforce the write and execute. So you have questions about especially the implementation on the guest side?
Yeah, so
can you go, for example, through the issues that you had with between V1 and V2 and why you made the changes?
Yeah. It should be, where is it? Okay.
So, like the static and dynamic memory permissions, is that something that needs changes in the module loader or in DPF? And also, if you like you said, we'll get them back on that later. So I suppose you have to say about that.
Yeah, I have a slide in that. Yeah, here. So yeah, we patched mainly the way they can map pages and change some page permissions. So with vmip, set memory X instance, and textbook. So that is set of. So for instance, when the kernel maps kernel memory, maps a kernel module. So in theory, we have everything to be able to check the signature of this, at least the executable pages. So that should be okay. But when there's, for instance, if trace or kprobes which change the kernel memory, the question is, how do we know if these kind of changes are legitimate or not? So can we get kind of a pattern of a set of changes that might make sense? Or how can we kind of restrict this kind of changes in a way that would not harm too much the guest kernel? So yeah, these are open questions. But eBPF, well, there's currently no way to check a program signature. So that is a really big issue too. We cannot, the LPC has no way to check if a BPF program, a loaded one, is legitimate or not. So, there were some proposals to implement BIF program signatures, but nothing upstream yet.
So I'm still starting to understand what we are trying to protect against for real. So the main thing you're doing with this hypervisor-based security is to protect the kernel from modifying itself, correct?
Yeah.
Okay. So if the kernel were to map itself, its text section, and the kernel maps its page tables of the fixed map as read-only, and then only has a small trampoline, which is the same thing you have right now with the hypercalls, a small trampoline to actually go and modify its own page tables, for example, in the cases where you need to, you could probably get 90% of what you're doing here without doing any hypervisor at all.
Yeah, but when it is dynamic, I mean at runtime, the idea is that the kernel might already be compromised.
But if the kernel is compromised, the kernel can call the hypercall that says,
Yeah.
I want to write to this now.
That's why we need to be able to authenticate these changes.
You do what?
We need to have a way to authenticate these new permissions. The data which might get executable permissions. So we have in theory everything we need for module loading, for instance, because we can sign module, and the hypervisor or the VMM, for instance, could get this signature and be sure that it is legitimate, and then let the kernel use this new memory, this new data, to make them executable. But yeah, the idea is to kind of delegate the trusts to something outside of the guest kernel itself.
I still don't fully get why you really do need all of that. Like I think getting us a 90% solution that just works everywhere is going to be much nicer than a 20% solution that is going to need a lot of adjustments in the whole stack, right? So if you're saying you need an authenticated path, that authenticated path can be part of Linux, right? The modular is already part of Linux, and then you just need to find a way. Like the thing you're concerned about is things like blockchains or arbitrary memory modifications of, I don't know, something, not sure what actually. So as long as you can't modify your text, and your text always goes to the same path to validate that the code it's trying to modify is signed, I even with everything in the same context, I don't see a way how you would easily, at least, without a complete disastrous security issue, circumvent it. And that, again, gives us 90%.
Yeah, okay. So that's a good point. But all this kind of control flow is, well, kind of comes from state data, and this might change over time. So even if you're using kernel helper to change memory protection, this could also be used by attackers. They can call any kernel code, jump to any kernel code functions, do some warp, whatever. So yeah, the idea is for attackers could execute all these kind of memory permission changes requests.
Sure, then you have CFI, and you
Yeah.
do add some operations to your compilers, or even just to parameter checks to make sure that the ROP chain doesn't know the secrets you have to hand over between your actual safe chain. I think they're just much more easier ways. And then once you have that and the kernel is self-protecting, then you can start moving pieces out to the hypervisor in order to even increase that protection.
Oh yeah.
Right? But I think we're starting at step 2 before we're doing step 1.
No.
You can go, Sean.
I mean, the kernel self-protection features, including CFI and such feature, are kind of a prerequisite. We need to have that but this is a step forward. It is an improvement of the current situation.
But we mark the fixed map as read-only for kernel text.
Yes.
What is your concern then with modifying that? We do mark the fixed map on read-only for the page tables that back the fixed map.
Well, if we can change text of the kernel, we can execute like anything, right?
I think the question is, what logic can you do in the VMM that you can't do in a protected part of the kernel?
So, the The main point is that at some point, the kernel can become malicious. But the idea is to kind of limit what this kernel can do.
Yeah, but what I'm saying is, so like you have a magic hypercall that lets you change permissions. The decision to allow or disallow has to have some magic sauce to it. Why can't you put that magic sauce in the guest, but protect that region of guest memory so that you have integrity of your decision making within the guest?
Okay.
And then you don't have to bleed anything out to the host.
Yeah, that's so. If I understand correctly, so you're suggesting to kind of put the verification mechanism, at least the verification code, into the guest, but we need to have some data, something to. Well, I agree that we need the hypervisor to do this check, this verification.
Why can't that be done? Like, what's so special about that?
The hypervisor is more privileged.
So I think maybe one way of looking at this is thinking of it in terms of how many places are there in the kernel that could perform operations that could potentially affect the page tables? And can we implement perfect CFI there? And if the answer is we can implement good CFI, but not perfect CFI, then arguably having this in the hypervisor allows us to have a sort of more constrained set of entry points for these modifications. And it's a more straightforward problem to do that in a space where the attacker has no ability to influence what's happening there, other than call into it.
The part I'm missing, though, is if you were bouncing out to the hypervisor, there has to be a hypercall. There has to be something to get you out to the hypervisor. That something has to, I mean, it's going to be a dumb pipe or it's going to be smart. If you make it smart, why not make it smart enough to just make all the decisions itself? Because you can protect what it's running from. Like at that point, is it just a data issue where you have more data in the VMM to make the smart decisions, and then you don't want to shove that into guest? That's the part I'm not catching.
There's one thing I can think of that the hypervisor gives you is a guarantee of logging and measurement. So you do have the ability with this to have an accurate log and measurement of all the modifications that were made, which means at least you get a bit of post-mortem ability or auditing ability, or in some case, verification. That's one aspect.
But I mean, the logging thing, then you have a pipe to just send out your stuff off the guest. Like, and we're rat holing on.
So one thing that I could see this happening is like, okay, CR pinning is nice. Memory permissions are important, but the way that you could do it in Linux, if you have this kind of enlightened guest, would be to delegate the patching to the host in a way where you tell the host the possible patching alternatives before you can be compromised. Like, I'm not saying this is a good idea. I'm saying that at least it tells you this is something that the hypervisor could do in advance. Or even like, I think there's maybe even more benefit from just protecting some data and making sure that that data cannot be written than actually even in the executable protection in some sense. Because let's say all the alternatives table, all the jump key, static key patching tables, if you can modify those, you could then trigger some kind of text, kernel text overwrite in a way that can be easier to sneak in. Like you first sneak in some change elsewhere, and then you actually perform the change. I don't know if this is.
Okay, so one of the And one of the principles here is that there is a security boundary between the hypervisor and the kernel. And so what this does is tries to utilize the security boundary and put security policy and decisions in the hypervisor, so that by principle, an attack on the kernel is not easily able to modify that. And so this is the same as like when you have user space. You could make a lot of arguments that user space should do all of its own security and resource management, but we have a security boundary between the kernel. So it's not an either-or thing, and we want as much hardening in the normal system as possible. There's already projects around this, the KSPP project and others. So this is more about utilizing a security boundary to kind of deterministically or more deterministically block certain classes of attacks, which we don't necessarily know about. So I think anything that we can do in userland should also be done as from a layered security approach.
Just to add to what James was saying, so I think as soon as a policy, because you haven't emphasized, you were talking about our hypercalls, which are going to change the policy, but if you can minimize that and pre-provision the policy into the trusted hypervisor, then and maybe some just leave out some things like like JIT and stuff even out of picture for now, so just let that be writable and things like that. So to minimize the policy changes, then the pre-provisioned policy to hypervisor can protect much more. And when we it's little transitions you can have between the what guest is asking to do. I think there is value in that.
So also, I'm a little less pessimistic than some of you in terms of the value this brings to the kernel, as you may have noticed. But I think it's also worth remembering that this sort of infrastructure, where it has been deployed elsewhere, has not just been used for the purposes of kernel protection. Having this sort of scenario means that you also have the ability to have additional guest hypervisors, VMs alongside the main one, and the hypervisor is then effectively a strong boundary, such that if there is a kernel arbitrary read primitive, then this may not block that at the kernel level, but if we can move all the credentials out of that kernel into a separate VM, then this hypervisor is now enforcing a meaningful security boundary there, and that is something that we can't just do by fiddling around with the kernel itself.
There are better ways to do that. Yeah, there are way better ways to do that.
And I think that's what Paulo was getting at very early on, of the guest changes for this are what are more controversial. From the KVM side, none of this is scary. It's not complex considering all the other stuff. But when you're talking about, I'm sliding up there, all the K probes and all the patching that goes on in the kernel, figuring out when that's safe and when that's not safe. And that's going to be like, if you're trying to upstream this, that's going to be your long pole by a huge margin.
Well, that's a very simple question. Like when you say set memory X has to be tracked, how do you know that that's a good one versus a bad one? Because you're going to allow them somehow.
Yeah.
How do you know that? You can patch it, right? But how do you know when you reach that point, whether it's the valid case or the bad one?
Yeah. It's also what Elena was saying, like there is value in putting a security policy, but what is the security policy? Like I made a stupid suggestion of putting the alternative tables. The alternative tables are a kind of security policy. So this is what we need to do first. Like start from what she said and say, what is the security sensitive thing that you want to move in hypervisor, and what's the additional protection that you get from there?
To the point about the concern about what complexity we're adding to the hypervisor to implement the security policy, if we have the ability to irrevocably set permissions on pages, we can make sort of an unpatchable region of kernel text, where we can actually delegate the policy to the guest, right? The guest has whatever logic says, these are valid ways to patch the kernel, or whatever the authentication necessary is to say this is okay to set the permissions. And then you lock down, those pages are read-only irrevocably, and then that becomes sort of your policy that you set up inside the guest, and then you don't have to worry on the hypervisor side about that policy being different for different kinds of guests, or how to send that policy to the to the hypervisor, you say only that unpatchable region of kernel text is then allowed to set these permissions for other parts of the address space.
Definitely.
But that's still a policy, right? Like, what is the workable policy that you need to do in there to say that, this page will never have a bit of BPF text? I mean, they come out of that state, right? If they're allocated in green, so you can't, I don't know what the policy would be.
We have a lot of static provisions and locations which are not going to change.
Look, that's the easy side, right?
Yeah, I'm talking the stack from easy side. The complex side is
All right, I think we are 1 minute away from time. I think the.
No,
I mean,
we had some buffer.
oh, yeah, buffer. Great. We can go over. Yeah. I mean, just summarizing, even though we have a little bit of buffer, but it does sound like we got to sort out what the guest side is going to be and how the policy is going to work. Because again, I mean, just beating a dead horse, the KVM side, not scary. But like, as you saw from like Peter Zylstra's responses to the few patches yesterday, I think people don't see the picture.
Yeah.
And, you're not going to get constructive feedback. You're going to get people just yelling at you.
So one thing I think I've been thinking, I'm pretty new to Linux. On Windows side, there has been things like, aliasing attacks. So how does this protect against like aliasing attacks where you can just map a linear address to a different GPA?
Yeah, so that's why we have a new data structure, which is this one somewhere. So we have a kind of we use counters to this one to track the mapping and kind of reflect what the hardware does and keep that in sync to know if there's multiple pages, physical pages, which are mapped multiple times with different permissions. And well, in this case, because we want this to work, of course, well, we get the union of these permissions, and that's it. We have the minimal required permissions. If at some point these pages are only mapped in a read-only way, for instance, we'll be able to not allow read-write mapping.
I can just write page tables to point a linear address to a different physical address, right?
Yeah, that's
so how are you
mapping.
checking that?
Yeah, but you also need to set permissions. And here, one thing to keep in mind is that there's the mapping, which is handled by the guest kernel, and this first layer of permissions for this mapping, and another layer set of permissions handled by the hypervisor and by the EPT CPU feature is only on the physical pages. So on this layer, we can enforce permissions, and
Okay. It's more of a comment just on the policy side. So this is a separate work stream that we're engaging with. There's a talk tomorrow more generally on this project. But the policy, so the idea, the expectation would be that there would be a secure boot, and as part of that, there would be a HECI policy would be loaded, which would be independent. So this is not something that would be hard-coded. And currently, we're parsing the kernel map to get mappings and at boot, so that we know ahead of time. On the static side of things, the dynamic side is more complex. But just to mention, the policy side is a ongoing development.
Yeah, so I think we can wrap up. Okay, it was the first KVM session ever, so some screw-ups were kind of expected, but I think in the end it got a lot more productive. So thanks to everybody that participated, and we can move on to the next session. Thank you, Michael. No, it's there. Yeah, you just have 2 slides, so it's easy. So you have like a couple of minutes, 1 minute before you start. So.
Okay. Can I from here?
Yes, the button there, right to the plus.
This is the farthest the mouse goes on here. I think that might be controlled back there, right? Oh, on here, you mean?
No, this.
Ah, thank you. Never presented from PDF before. All right, 10:15. Should we go? All right. So this is a quick, we should do introductions first. I'm Anish. I'm going to present a proposal for multi-KVM. I'm going to walk everyone through the what, the why, the how. Should probably just take around 4 minutes. I just have 4 slides, and then I'll open it up to questions, which is really the whole point. So yeah, if you do have questions in the middle of the presentation, just hold off. It's not going to take very long to get to the last slide. Okay, so the what? So the proposal is to allow multi-KVM, which would be running multiple independent KVM modules on a single Linux host. Why would we want to do that? So we can upgrade and roll back KVM with minimal disruption to running guests. They would also allow running KVM modules with the same version but different command line args on the same host. And that also allows easier testing, A/B testing on the same host for KVM. Sorry, this slide doesn't move. Okay. So how we propose to do this is there's a bunch of steps. Some of them have already been started. So the first is isolating KVM internals from the rest of the kernel. Sean already has a patch series out. This is something we would like to do even if it doesn't lead to multi-KVM, because it's just good design principles that go behind the patch series itself. And then to move on to running multiple KVMs on the same host, the first thing would be to collapse vendor modules into kvm.ko. This allows us to expose multiple KVM-N modules and multiple dev KVM-N devices without having to worry about the exports that the vendor modules require from KVM, and they won't have to be versioned. In this case, the KVM-N and dev KVM-N postfix is defined via a config string. By default, we want that to be null or off, so it shouldn't change the status quo. If you opt out of the feature, you would still get 1 KVM, except this time it wouldn't have vendor modules running on top of it. We would introduce, therefore, a new base module, which KVM, the new KVM would run on top of. The name for this is Virtualization Acceleration Code Unupgradable Units, which is a bit of a mouthful, mostly a backronym from vacuum. It does suck. So, yeah. So that would be the new base module. The point of this base module is to have shared system resources that cannot be in multiple KVMs running on the host, because they would just clobber over one another, and they need to really be shared between multiple modules. And then the goal here is that user space should mostly be unaware of these changes. So making symlinks between dev KVM to dev KVM-N or using bind mounts should mean that user space VMM changes should not be required. It should essentially just function the way it does today. And all deployments and which KVM would work on what kernel is not really the responsibility of this project. That's something that deployment, whoever controls your deployment, would handle on their end. Okay, so that is my presentation. I just was going to bring up a few things that I think might be good to get feedback on, but it's not limited to this list. So hiding those KVM internals from the rest of the kernel, that's something we would like some feedback on. Module name, it's always a sticky subject. Nobody likes naming. I'm bad at naming. It's not even my name, to be honest. But and then collapsing those vendor modules for x86 into KVM. I would like some feedback on that if people have thoughts. And then anything else people want to talk about.
So can you go into a bit into more detail of what would be in the maze module? I mean, I assume it's the one that actually calls VMX on, but I guess it's a
Yes,
bit
that
more-
is one of the things it has. So hardware enable, disable logic would go in there. The goal in principle is to minimize what goes into the VAC because that's the part that you cannot upgrade. So the principle would really be to minimize that. And it also has a list of VMCSs, VPIDs on Intel. Yeah, Sean, you might have more.
Yeah, so hardware-wise, ACIDs on AMD, VPIDs on Intel. So anything that you have to have a singleton throughout the entire system, that base allocation management would go in back. It would also serve as kind of a mediator / trampoline so that the core kernel doesn't have to be so aware that there may be multiple things sitting on top of that back module. So like perf callbacks would be one where you have the back register a perf callback. So perf doesn't have to walk through a bunch of different things saying, hey, are you the right KVM? Hey, are you the right KVM? We just have one call. So we mediate some of that stuff. User return MSRs on x86 is another one that ideally would go in back because then there's some nastiness there with capturing state in IPI handlers, which you can accidentally snapshot a guest MSR instead of a host MSR if you take the IPI at the wrong time. Other things. But yeah, the base principle is if it can stay in KVM, we want it to stay in KVM so you can upgrade it and you can change the behavior.
So the kind of the elephant in the room is like all of these multi KVMs would be out of tree modules. Like they would be out of tree in the sense that they are compiled for multiple versions of like KVM itself, like linux.git itself would contain only one KVM module because, yeah. So the question is, do you see a use for the VAC outside KVM, like other uses of virtualization facilities in Linux that would kind of justify the existence of the VAC?
We do not have any planned, and I can make up use cases, but I don't know of any that are actually that anyone actually wants to push forward.
I just want to talk about the motivation of this. If I understand correctly, it's basically about live update, right? You want to be able to, you've got your old KVM, you now want to switch, you want to run your new KVM, right? That is
It's one of the, yeah.
This one, yeah, it's all just made up. So live update is actually something we are not sure we want to pursue with this because you get into a matrix of kernel versus KVM modules that you have to validate, and that just makes everyone cringe. And so the other way that we're looking at this is for deploying new features, because then you can say if you've got base kernel X, that's your minimum for supporting this new feature. And if you're before that, you can't get this new feature. And then you limit your test matrix because you're not trying to upgrade every kernel in your fleet with this mechanism. You're just trying to roll out new features to specific base kernels or even specific platforms. And then use things like live patching, or, I mean, that's the big one, is if you have security fixes that you need to roll out somewhat quickly, use other mechanisms for that. We're not completely ruling out live updates in terms of using multi-KVM, but we're also not gung-ho on it because...
Yeah, I mean, you could still use it if you have a better validation strategy, but it's not something we are particularly interested in.
I guess what I was trying to figure out is if we had a good solution to live update, would we still need this, or would we actually then use
for feature rollouts?
Right, but you could do feature rollout with live updates, right? And then you end up in a state where you don't have to run all the KVMs at the same time because your old VMs are still running on the old version of KVM, right?
What do you mean by live updates? I think that's what we have to clarify.
We need another one of these. But basically, the ability to update your entire hypervisor, right? And that's another thing where I think you're going to hit limitations of this pretty soon. Where you're like, okay, I can update my KVM module, but the rest of my kernel, I still need to do live patching or something, right? And if we had a good solution to
Sean,
live
why don't you
update-
just come up here? You can use this mic
Yeah.
and that way. Yeah.
If we could just update everything, I mean, isn't that a preferable mechanism? It gives you the ability to update your whole kernel, not just KVM.
Oh, I mean, in a perfect world, absolutely. I'm not convinced that we're going to get there in the next 4 years, though. To get to a point where we can achieve the same level of downtime with, if you already have your other KVM instance there, and you're not going through kexec, you're not spinning up user space again. I mean, even if you get the full kernel upgrade to a point where it's acceptable, I would assert that you're still going to have a longer downtime than what you can achieve with this.
Well, this has no downtime because you're not actually upgrading, right? Your old VMs are still running on old
If you go with-
KVM.
You live migrate to the other KVM, right?
If you use this mechanism to do if you use this mechanism to upgrade a running KVM, which that's the part that we're like, yeah, we're not sure we want to do. My point though is they are overlapping, but I don't see a full kernel upgrade supplanting this entirely, because it can't, I mean, you're never going to be able to get to a point where you have zero, like literally zero downtime. It's just not going to happen. You have to run some code. Like you can hide, you can play a lot of games to hide it.
How
But
many CPUs do you need for that?
what's that?
Yeah, but how many CPUs do you need for that?
Need for what?
To run that sum code.
Oh, no,
That's
like,
different stuff,
yes, and
right?
you
But
can keep
hey,
it running in the
let's set
guest.
up all those secondary CPUs and have them do
Yeah, yeah.
nothing and then bring them.
Oh, yes. No, I'm in total agreement that the ideal goal is you keep the vCPUs running in the guest while you're swizzling bits on the host. But again, I don't think that that is something that we can, especially internally, I don't think we can achieve that in the next 4 years, realistically. Whereas this is, for us, at least a stepping stone. The other thing that, from like an upstream hat on that I like about this is being able to test different module parameters. And then that pushes back on things like we want to run one VM with mitigations disabled and other VMs that we don't trust with full mitigations enabled, like the NX huge page disaster that I despise. We have a capability so we can turn it off per VM. I was like, that shouldn't exist. Like,
but that doesn't have to be module parameters, right? That can be VM parameters.
It doesn't have to be, but it simplifies KVM. Like the reason we don't support, we could theoretically support shadow paging alongside EPT. I don't want to support that from an upstream perspective of, oh, we have, like, it's nice when you can just look at the module, you have TDP enabled or you don't have TDP enabled, and you can have a whole bunch of decisions on that. You don't have a per VM pointer that you're dealing with to decide what set of all that things I'm using. So it's chewing on different complexity to achieve multiple things is the idea.
Yeah, so in that case, it's not actually about live. It's not actually about updating. It's actually you want different flavors of KVM running next to each other on the same host. And you want to be that, at the KVM module level.
Yeah.
There's a question. I think Oliver had his hand up. No? Okay. And then something on that side.
Hi, this is regarding the isolation that you have over there. So later we have a talk about sharing more details between the guest and the host, especially on the scheduler front. For example, VCP is preempted. So those kind of, there are some scenarios where we would like the host to have a better understanding of what happens inside the KVM to make better scheduling decisions, memory management decisions, etc. So by this, we might be compromising on that, or
yeah. So the idea here isn't to say the host can't ever talk to KVM and vice versa, but that when we say isolation, it's isolating the gory details of KVM. So right now, struct KVM vCPU, a whole pile of stuff that should not be exposed to the kernel at large is all visible in KVM host.h. And so there are details bled everywhere. And that means if you wanted to change the layout of struct KVM vCPU in any way, you're risking something in the kernel having the offset as X, and then you change to X+2, and things blow up because you're clobbering KVM. So that's what we mean by isolation. We're not saying that thou shalt not talk. It's just really the details of things that shouldn't be exposed, and then have proper APIs when you do need to talk between the core kernel, or like KVM GT needs some hooks into KVM. Just have very well-defined APIs for when you're moving stuff in and out of KVM to the rest of the kernel.
Although with KVM GT, that makes it mutually exclusive
For
with
this
multi-KVM.
because
but
no one
yeah,
wants to use that. Yeah.
Okay, so if I understand correctly, we'll have some opaque handles that the other parts of the kernel can use with an API or something to get details.
Yeah, I would have to, I don't know exactly what you have in mind, so I'm not going to commit either way. The question was, do you want to get guest information or KVM information?
The guest information through the KVM module to the scheduler. So yeah, it's basically some information from the guest, but that's KVM is providing that through shared memory. So yeah, that's it. Thanks.
I think we have. Might also be out of time. I don't know how long this talk is.
Apologies, he's back up today.
Hi. So I have another kind of high-level question about this. Is there any prior art? Are there any other kernel modules that do support some kind of, multiple versions at the same time? This doesn't seem specific to KVM, so I'm curious if you have investigated it or if anyone else in the room knows about any of these kinds of solutions.
To my knowledge, there's nothing in tree. Out of tree, people have done this exact thing to varying degrees. And I'm guessing out of tree, people have done all kinds of crazy things, I can guarantee. But as far as what's been upstreamed, I don't know of another use case like this.
Okay, thank you.
You talked about combining KVM Intel and KVM AMD into KVM.ko. Does that extend to other architectures as well besides x86?
No, so this is purely an x86 wart. The downside to dropping them into the single KVM module is just your text increases. You get a small benefit today if you're running on Intel. You don't have to load KVM AMD, so you save that text. That's really about it in terms of what you benefit from it. As far as other architectures, this is almost purely x86. The only thing that affects other architecture is hiding the internals. And that one gets a little bit ugly because like ARM and S390 need to get at some offsets in KVM vCPU so that they can feed those into KVM ASM. And that was how we ended up. If you look at the RFC, it was just if-def shenanigans instead of any invasive changes.
And it's going to be kind of a heavy lift to be able to load text into EL2, like for the NVHE use cases for the ARM. It's not like running in a kernel context anymore, so you need to build your own way to load text into there as well, which would be kind of a pain.
Wow.
Is it left?
So actually, mentally, I had read that as collapse KVM.ko into KVM Intel and KVM AMD. So why would you have one module for both Intel and AMD instead of linking the common code twice into the two vendor models? And actually, maybe there is not exactly the same thing, but there is a precedent for KVM on Power where you can, like Alex, correct me if I'm wrong, but I think you can have both the hardware accelerated virtualization and the trap and emulate virtualization. And they are two separate modules, I think, and you can only load one of them at a time. But in principle, you could have both of them active at a time. Like
so
some VMs running under tap and emulate and some VMs are running under
Yeah. I mean, we're going to end up with that on x86 for Intel with TDX versus VMX to some extent. They're not going to be separate modules, but you're going to be running two flavors of virtual. I mean, that's what you have on PowerPC, though. You have two different flavors of virtualization running side by side.
Yeah, but on PowerPC, there are different modules, so you have to choose the one that you load.
Yes.
So you cannot have at the same time on a PowerPC host both the hardware accelerated and the tap and emulate virtualization active. So
I guess, yeah, so
Like,
essentially it boils
10 years
down
ago,
to-
there was actually a good use case for this thing. But so going back to the other question, why would you fuse the two modules and not link the same code into two of them?
We just didn't do it. I think from a code perspective, it'd probably be quite, if we want to go in that direction, I think it'd be very easy to, I mean, it might even just literally be the make file changes.
Yeah.
It would make life a lot easier because you don't. It will make life a lot easier because you don't need to go through all these indirect function lookups, right? You can literally just link. It would simplify the code tremendously between the AMD and the one. KVM upstyle.
Yeah. I don't know that it would actually simplify code. You would still need vendor hooks. They're just going to be resolved at link time instead of. Yeah, but we have everything static patched. Oh, like I agree from like it, but I think the amount we would move the needle is actually quite small. Like I'm fully on board. I'm just playing devil's advocate.
I want to ask, because you mentioned one use case for security, so that you will be running with multiple modules, and one, let's say, would be more, have some security update on, or some have security features, so it would be kind of more privileged, or I don't know, more trusted, and then another one. And now the question is, if you wanted to have that, do you have mechanisms in place to actually start isolating this? Because now you will have this core, which is like, unmovable, and then one module which is less trusted, another which is more trusted, and they're gonna all talk together. And if you don't have isolation, you don't have boundaries. So, this fact that you're doing it is.
It's not that the use case isn't that one KVM module is more trusted than another. It's that the workload that is running inside the guest, specifically the kernel, and it's not even, I wouldn't even say it's more trusted. It's that the performance versus risk trade-off is different. So large VM, big customer that is paying a lot of money, if they start attacking with ITLB multi-hit and start crashing hosts, and we see it's coming from their VM, we can be like, hey, large customer, you're really screwing up. We're going to start charging you a lot of money. So we can turn off that mitigation for those VMs versus a VM that's being spun up for someone that is like just running one-off VMs, and we don't have as good a paper trail. It's not that we trust them any less or anymore.
It's not. It's not.
But the risk versus reward of letting them potentially crash the host isn't there because they're not paying as much to get better performance.
Okay, so it's not for fixing security issues potentially in KVM itself.
No.
Got good mind.
This may be totally not at all where you want to go, but just out of curiosity, is there any chance that you could use this to implement address space isolation where every single VM has its own KVM?
I don't think that, I think they're orthogonal.
Okay.
Because the address space isolation isn't so much about the KVM instance, it's about literally the address space. And so KVM, today requires that you have, that you can only do the interesting ioctls from the process that owns KVM, that originally created KVM. There's some mem slots stuff that bleeds into the address space, but other than that, KVM is quite oblivious, and MMU notifiers. But beyond that, KVM doesn't really talk address spaces today very much. And so the boundaries where you need the address space isolation are more once you get into the host, and then you take an interrupt. That's not KVM at that point. That's core kernel code, and you need some boundaries there.
Yeah, the boundaries can be defined. I was just wondering if this makes that potentially easier. I know there was a patch series for that like a year ago, I think, or something.
Yeah. I don't think it makes it meaningfully easier because getting it to work in KVM is the easy part. Getting the rest of the kernel to be performant when you're switching between the address space you're using to trampoline into the guest and the address space you're using to service all the stuff in the host. Those are the boundaries that are tricky, and almost none of those are in KVM.
Yeah, I have one question about these. I think one of the things I like you meant is like
if we have a multi-KVM kernel modules, it is easier to fix some non-trivial security issues. For example, something, not necessarily all of the things that we can be live patched. Some of the functions, due to the limited size in the text, right? We have, with multi-KVM, I think this is much easier to do. You can modify basically arbitrary code and recompile. One thing I would like to raise is like, if you want to do this, is it really should be done in two phases? Where one is like you have to separate the common code, like access to those resources that is common to all of the KVM KOs as a step one, and then go to step two. I mean, the step one might be one stone to bird, which allows open up the capability for other hypervisors to hook in. I mean, as well.
I think that goes back to Paulo's question, though. Is there a use case for that we'd be enabling? From within a series to enable something like this, yeah, it would be two steps. You do all the prep work, and then you do some of the gory enabling in the back half of it. But in terms of accepting code upstream, unless there is an actual use case, if we did all of the isolation and collapsing of modules, we'd be doing a lot of churn, taking on a lot of complexity, and changing behaviors without any good reason. So I think from an upstream perspective, it kind of has to be all or nothing, except for maybe the isolation part that has value, in my opinion, irrespective of the multi-KVM stuff.
That time?
Glad he doesn't have something to throw at us.
All right. So the next speaker couldn't be here. So for those in the audience that don't know, we have a bi-weekly sort of call of upstream KVM developers. So he has to move his discussion to that occasion. But we have Alex and Ben and others that have provided a replacement. So if any of them want to come and explain, and they are experienced developers, so I'm sure that they will be able to do it without slides and without anything.
All right. So this isn't formally a KVM thing. It's more of a VFIO DPDK thing. Doesn't matter. Irrelevant. It's a request we've had from people left, right, and center over the years to be able to specify that the mapping of a portion of a bar into user space through VFIO be done with right combined attributes. We can think of potentially a generic way of specifying any form of attributes, but right combined is the one people are today interested in. And so there was all discussions and RFC patterns and stuff floating around for a while. Just an open discussion here, what would be the best way to do that? I was thinking of using the existing, God, I forgot the terminology now off the top of my mind, but VFIO already have a concept of regions. Some are fixed, which are basically the bars, but some can be dynamically added. And today only dynamically added by device-specific backend drivers in the kernel. But because it's dynamic, we could extend this. And so the idea was to have IOCOTLs to create aliased regions that represent a portion of a bar with a different mapping attribute. And then the open questions are what's allowable, because every architecture has different rules when it comes to multiple mappings and conflicting attributes. Do we need to unmap the equivalent portion of the normal bar or not, etc. So there's a bunch of skeletons that needs to be dug out of.
Yeah, so the reason why I asked if it's in a guest, because as soon as you run a guest kernel, it can also apply its own attributes in terms of PAT or whatever. And that also complicates the possible conflicts across different mappings. So for example, right now, KVM is not really allowing any of the guest attributes. Okay.
KVM allows write combine.
For the KVM guest attributes, though, that's something that we really need to look at because they're horrific. The MTR stuff should just be killed because there's no use case for it. And we should just allow pat, period, because there's actually no danger if we do things right.
Yeah, so there's architecture-specific issues here. I'm not totally familiar about how the x86 KVM general case does it. I know. I'm pretty sure we allow attributes modified by the guest on EC2 with Brimstone. I'm pretty sure we allow it on PowerPC and an ARM as well. The way the memory types interact with each other, extremely architectural or even implementation specific. So it's a little bit nasty in that regard. But yeah, I mean, the request is from customers who want to use things like DPDK and basically want to be able to use write combine when they write short messages in the message buffer of the device. They don't want to use DMA because it's low latency communication. So we're talking about message passing type of adapters, that sort of thing.
Ben, you said a portion of the bar. You want a portion of the bar to be write combining, but not. Is that really a requirement? Why a portion? If you say the whole bar, it gets quite a lot easier, right?
So I don't know what specific requirements the last people who talked to me has, because it's again very adapter specific. So I do remember from some Mellanox things from years ago where the write buffer was somewhere in the middle of the same bar that also has the programming registers, which must not write combine.
Yeah.
So and in fact, there was not even a 4K boundary or anything like this. So you need two mappings, one to access the registers and one to do the write combine stuff. The difficulty, of course, is write combine is not semantically well defined across all architectures and all implementations. On PowerPC, for example, we take out the Gbit. That potentially also mean prefetch. Which means now we have that second mapping that also happens to have some programming registers in it somewhere else. Technically, the CPU is allowed to speculate and prefetch. Practice, it doesn't, or at least it didn't. And nobody cares about PowerPC anymore anyway. But yes, there is interesting issues around even the basic definition of what write combine means. It's not always clear for all architectures and all implementations. So I don't have a perfect answer to everything. I know there is a requirement that's been around for a long time. People have been annoyed not being able to write combine on these things. Food for thought. I mean, I haven't had time to work on this before today because I was doing other things, but I was going to do an RFC patch at some point along the lines of what I described earlier. And
quick thing. So if you do write combine on some register, you will break a bunch of driver, because driver have like, you need to write this register and then you need to write this other register, and you cannot combine the write, otherwise you get side effect that you don't want. So.
And I was just going to mention that it's a question of who knows where to write combine. Right?
Correct.
So,
but ultimately it's the driver. In the DPDK case, it is the user space driver.
So if it's a user space driver, it makes sense that we can have a separate region. That driver knows where to do the write combining. In a VM, we really only need the one region, and the guest via the MTTRs or whatever knows how to map that specifically.
Yes, and I mean, and then you can pass through the entire device into the guest, and then the guest itself could use DPDK with VFIO inside the guest and modify the leaf attributes in the guest page tables or MTRR if you can do that. I don't know how that works on x86, but yeah.
Yeah, I was about to suggest like just do two completely separate mappings, and it's up to user space to know, do I access the right combining or the not right combining? But yeah, the passing it through to the guest one is then more complicated. You can't
The
do
passing
that.
through the guest, I don't think matters in that regard. The host VFIO will just pass the whole thing through, and then inside of the guest is just the leaf page table mappings of the guest that will define the attributes.
Yeah, there's two considerations there. One, is it safe from the perspective of the host? So if you don't have concerns about aliasing memory with different attributes, either in terms of crashing the CPU or having memory corruption, then it's a lot simpler because you can essentially just let the guest do whatever it wants. That will take some arm wrangling of hardware vendors to get them to say exactly what is safe and exactly what behaviors are
Sure,
there.
but Sean, today,
We got some of that arm
the
wrangling.
guest can already do that today. I mean,
Nope.
we're not going to allow something that the guest can't do already.
Nope, not on x86. It's a disaster.
Yeah,
but the
well,
guest
then
can't
that's
do it.
okay. I mean, I'm not necessarily proposing that we relax existing limitation like this. Okay, well, but that's an orthogonal thing. That in the point, my point is the interface change I'm proposing are not related
But if
to
you
that.
bring in the guest, if you don't relax what KVM does, it becomes ridiculously complex, because then you are trying, if you don't say that having right combining the guest but not right combining the host is safe, then you have to explicitly disallow that. And that means you're either trying to shadow what the guest is doing with its page tables to prevent the guest from using right combining. You're either mucking with the PAT MSR in x86, you're messing with EPT tables to ignore the guest PAT, and it's a disaster.
All right.
If we can rule out all of that and say, this is safe, we don't care
Okay.
what the guest does, then it becomes
So,
much more of a non-issue.
In my experience, right combined aliasing tend to be safe in things I know about, but I don't know everything.
And this is why I want Intel and AMD to be like,
yeah,
this is safe. You
the
will not burn
one
your
you
machine.
really do not want to mess with like this is cacheability, because you can potentially crash the machine or allow the guest to uncover the memory underneath the caches, which we really do not want to do. So the one we don't want to let people mess around like easily, at least not in a guest, is cacheability, or even in user space. But right combined, in my experience, that tend to be so. But yes, we should try to get somebody at Intel and AMD to sign something in blood.
So Intel and AMD are also different because Intel has a bit to say override the guest's mapping, so it's easy. On AMD, there's like a kind of three-dimensional table of guest PAT, guest MTRR, host PAT, whatever. And I know that we had both issues where things were too slow because it got uncached instead of write back, and things where we got machine checks on Intel because it was not using the right mapping and it was causing conflicts.
I am 99% certain that the machine checks were not due to conflicts. It was because the patches that allowed the guest to map whatever it wanted with whatever attributes it wanted allowed it for host MMIO, which meant that the guest could access host MMIO with write back, and that will machine check. If you access, say, your APIC through the MMIO mapping with write back, that will immediately machine check. And I think that's what the historical problem was, that we worked around in KVM by saying, we're just going to completely ignore whatever you want. That's the restriction I want to remove. The other thing that we have really messed up on x86 is the MTRRs, which we honor on Intel, but not AMD. And I'm 99% certain that is also a hack around for the machine check problem and not digging through everything, because the only reason that you would honor the MTRRs would be to get UC or write combining for guess things that it wants to access, but it works on AMD and no one's complained for 15 years. So why do we need it?
Yeah, I don't remember, like I was just starting KVM at the time, but I remember that the machine checks, we were seeing them only with Mellanox patches to the driver that were kind of hacking and forcing the use of a white combining mapping. So there was something that had to do specifically with white combining. For AMD, I think it's just that the code for MTRR was contributed by Intel, and the particularly bad maintainer that didn't know what he was doing didn't notice that there was also something to do on the AMD side.
So I've opened a bigger can of worms than I was expecting here. I can't deal with that specific problem. I don't have the expertise for that. What I can do is, when I finally get a bit of time, whip up some RFC patches for the interfaces, IO controls in VFIO to enable doing those aliases, and we can continue on the mailing list. Figure out where we put some form of validation of conflicting aliases, which probably going to have to be an arc-specific hook, unfortunately. And how much we abstract? Do we just create an abstraction for write combine, or we have a pass-through for arbitrary attributes? No, we're going to have to hash that one out. Even if we don't solve the KVM problem initially, it's already going to be useful for metal systems using DPDK. So, yeah.
I wanted to point out, Will Online is just pointing out that ARM64 can actually speculate read on write combine. So if you have speculate read on write combine, it means you can have also clean write back some cases. So it will just wreak havoc on your register for your devices. So just pointing out that command online. So, you you really need to have the Intel, AMD, and ARM to tell you, hey, it's safe to do. Otherwise, it's going to be a real mess for the driver.
On ARM, you can. What is Will exactly saying?
ARM64 can absolutely speculate from one combine.
Yeah, well, a lot of architecture, I think, can.
The issue is if they do a clean write back. So if they do,
most of those devices we're talking about are fairly modern and sane, which means they do not care about reads, and they don't have. Those things, thankfully, tend to disappear these days.
I'm still seeing clean write back on some architecture. I won't name people, but I don't understand why I'm seeing still.
Yeah. I mean, the lot of devices are moving toward having prefetchable bars for that reason, and so they tend to drop the whole read clear and read side effects. But yeah, I mean, we can look into it. I mean, we could maybe, if it works for whatever the latest customer is asking, to just have a strict separation of pages at least, and non-aliasing for whatever the device they are using today, and ignore the ones who.
Yeah, but I think what we really want to see, at least on my part, is like make sure that device maker actually isolate this kind of range on 4K ranges at least. And
well, 64K is, I mean,
okay,
yeah.
Yes, 4K becomes an issue, yeah.
Or 16K on ARM. I mean, I can do a bit more and check, talk to whoever asked last and look what the device looked like. We could initially just 4-bit aliases, like unmap the original fragment of the original bar, or even make it whole bars. I didn't want to have an API that was limited to just changing the mapping of an entire bar. I thought that was too limited. But we could have something that if we create one of those subregions for a fragment of a bar, we actually unmap then the portion, the original portion. I don't know. We can look into it.
Engineers.
Let's say ongoing discussion might be.
Yes, we would have.
Everybody knows we need to get away. Also enables very minimal first stage is enabling the next. Also enable this. So in the beginning, trying to do this, what is our first step in device security? And then. No, I know. Really, it's yes. I'm trying to. So,
Yes, right. Yeah, no. Well, it's also so on the KVM will have a stronger brand. So it's going to Yeah, okay. Yeah, this professional. That's something to do with wow. So yes, very much again, it's very rich. So it's really rich from my professional. There is no perspective of that. Now, professional things get from that. I think it's already. But it's very important. It's professional. Yeah. So. This is about
Yeah, I know that you did. No, they are here, so that's fine. Okay. It's fine. I mean, yeah. No, he got it from the acceptance email and everything, and I think the discussion was correct. It's just
Yeah, it was good. Yeah, I'm glad that we got this.
I think the discussions went well. I mean, Elena made a very good point, and
I think this is exactly what we're
exactly like
people to.
yeah.
When did you download this?
This morning.
Do you mind just pulling it again?
Sure.
I fixed something that had explained.
Okay. How do you do that on a Chromebook? No.
What you're doing is downloading it from the website.
I'm downloading it from the website. Yes. That's the only.
Yep.
I mean, that's what we were told. So there's no alternative. And then I have to. I have already downloaded it.
Oh, we kind of changed it.
Okay, then. Sure.
But if you just hit refresh, the new one will come. Right?
Yeah. So have you uploaded it already?
Yeah.
Not sure webcam. Is it? How do you?
Yeah.
Oh, you have PPT?
I can convert it if you want like that.
No, I think it's fine. No, you have to send to upload the PDF.
I'll do it in a second.
Yes, sure. Yeah. There's 5 minutes buffer, so it's fine. No problem. Yes.
All right. Good morning. Thanks everyone for coming. I'm James, Kernel Engineer from Amazon EC2 with my colleague Alex. And the discussion we want to have today is about live updates. So this is something that has been discussed quite a bit. Even the KExec session yesterday was talking about live updates. And yeah, so we want to figure out what the right way is to pass kernel state across from old kernel to new kernel so that you can boot KExec, a hypervisor, and keep virtual machines mostly, keep some aspect of them running during that KExec. The technical implementations here is going to be in PCI and IOMMU and KExec, but I think the reason that KVM MC is the right MC for this is because the use case is all about virtual machines. It's how do we update the hypervisor, and so it's thinking about the KVM use case specifically for this. So this is roughly what we'll do. We'll look at what we can do today, what we can't do, possible ways to solve it, and then have a discussion. So live updates, you can kind of do it today. You can carve out a whole bunch of memory as reserved memory. You can run QEMU, get QEMU to use a file in that preserved memory pool, like a DAX device for guest memory. And you can also serialize state and put it in that pool. And then after KExec from kernel A to kernel B, QEMU can start up again. It can use that same file for guest memory. It can read out the state and put it back into KVM, deserialize the KVM state. So you can kind of do that today. What happens if you want to do device pass-through? So you've got a PCI device, you want to assign that to the VM using VFIO, and now you do KExec, okay? But that device is assigned, and it's trying to do DMA operations while you're doing KExec. That's when things break, because in order for that device to be able to continue doing DMA during KExec, you need the IOMMU page tables specifically to be left alone so that the hardware can continue to use them. And that's kind of the fundamental one of the fundamental things that we need to figure out how to solve so that we can do live updates. So we need a way to preserve device state so that we can do device assignment while we're doing KExec. That's kind of what we're showing with this graphic here. We've added this little contract or little text document to kernel version A and kernel version B. We need some way of having this kernel state passed from the old kernel to the new kernel. So KExec doesn't zap everything. It can kind of pass some things along and keep them there and keep it in use by the hardware during KExec. So specifically, like I said, IOMMU mappings is one thing. We also need, once your new kernel is started up, you need to kind of be able to pick up that state that was passed along. So how do we expose that to user space so that the QEMU process that starts in the new kernel can say, actually, I'm the same as the old one. You need some kind of way to expose this to user space. And we also want to avoid doing PCI probing, because that's destructive to the bars. You have to go and reread all of the bars. So how can we pass PCI topology across so that you avoid needing to do PCI probing? And that also ties back to the KExec talk yesterday when figuring out how we can do that. There are various other use cases that you want to pass kernel state across. Just another example would be something like SEV-SNP, where the hypervisor actually does not have access to the KVM state, right? It can't read it out, therefore it can't persist it. You can't serialize a SEV-SNP instance. So you need some other mechanism where you don't actually read that state out. You rather just kind of know where it is, and you pass that information across from your old kernel to your new kernel so it can continue using that KVM state, even though it can't actually access it. The hypervisor can't actually read that state. Yeah, and various others. So basically, you can kind of break these live update bits of functionality into correctness, where you need to be able to do this so that you keep running correctly. So IOMMU page tables and SEV-SNP states are examples of that. You have to do that. And then there are other things where can we make live update faster, KExec much faster, so that we reduce downtime by passing more information across. Some examples there. And so roughly there are three sort of categories or classes of proposals to how to solve this problem of passing kernel states across. I'll go into them in a bit more detail in the next slides, but just as a rough outline, the one class is we have a memory pool that lives inside the kernel, which is persistent, and kernel drivers and modules can come and allocate persistent memory from that pool, and then it survives across KExec. That pool is not destroyed. It's not managed by the buddy allocator. Another type is, it's similar to that, where you've got a pool, but you put a file system abstraction on top of it, and then kernel modules can access something by a file from there, and user space can do that as well. So yeah, user space can put guest state and guest memory in that pool using file handles. And then the third class is where you don't have pools of memory, but rather the drivers and modules are able to allocate memory as they do today. But just before KExec, you have serialized hooks where the drivers and modules can say, this is my state in my memory that I need to pass across. And after KExec, that state gets re-injected back into them. And there's also logic to know that the memory that's used by these modules must not be clobbered during KExec. So some way of carving it out of the allocator. Yeah.
Are these three mutually exclusive, complementary? Is there a vision for how these would fit together?
Yeah, so that's a good question. I think at the moment we've mostly been thinking of them as separate, but that's probably not the case. I think they're fundamental building blocks, like the serialized, deserialized framework. If you had that, you could then build pools on top of that, right? Where the pool could pass its extents across from old kernel to new kernel using the serialization framework. So I think that's kind of one of the things we want to figure out, like, are these composable? What is the right way to structure them so that they are composable? I actually don't want to spend too much time on this slide, but basically, these are examples of the memory pool that Microsoft proposed, two different ways of doing a memory pool. We, AWS EC2, are going to send out an RFC soon for a file system type of proposal. And roughly, I just wanted to sketch it out. It would look like this, where you would have this file system on reserved memory, and then kernel modules can store their state in it by file paths, and you can kind of use those file paths, which are actually reserved memory across kernels. And then the serialization one, I've mentioned that already, but yeah, it's a way, provide hooks, serialize your data, and get it re-injected. And one of the complexities here, see that middle line there, complexity. So one of the problems is because you don't have a clear separation of this is my persistent data and this is my ephemeral data, and you don't kind of know that up front, you can have persistent data anywhere in the kernel managed memory, and you have to then find a way to make sure that you don't clobber those specific pages. The new kernel doesn't clobber them. Yeah. Go ahead, Ben.
Yeah, there is a mechanism today in the kernel to quote serialize and represent device and potentially states that also happen to be in a single relocatable blob and not scattered across. It's called the device tray, the flat device tray more specifically. So you could initially generate some kind of pointer-based device tree and then flatten it at the end into reserved memory, and that gives you a single relocatable blob.
But it's not relocatable, because think of things like IOMMU page tables or SCV. You can't move that around, right? It's in use.
The representation is relocatable. You're not going to put the IOMMU table itself in a device tree.
Well, that's
the reference. Yes, you're always going to have some things that, yes, exactly. But you don't have a bazillion of string pointers all over the place. That's my point.
Sure.
Like all of the little driver states, all of those little things, all your PCI devices and all of that jazz can be nicely set in that big contained blob.
All right, quickly, just to preempt that. Yes, I agree. We basically have a fundamental concept of metadata and actual blobs, lots of blobs of massive data, which can literally be, I don't know, hundreds of megabytes of page table data, right? For example. And I think we need to look at these slightly separately. What James is referring to is, should we be smarter? And I think that's also what Sean was trying to get to, right? Should we be smarter about putting these massive blobs into something that is essentially like a treasure box to pass them over to the next world, that we already know is a contiguous amount of memory, so we don't have to go and have like hundreds of thousands of 4K entries that we then go and parse left and right. For the metadata, I have a POC right now that is on the list, not really, it's only the link to a patch that is semi-functional. But the current thing, the way I'm thinking of this is exactly that device tree, right? So the serialization path, I think this is part of your serialized slide as well. The serialized path creates a device tree, not the device tree, the data format of device tree. It uses libftt to serialize itself. It uses libftt to deserialize itself again on the other side. Yeah. And by doing nomenclature identically, right now I'm basically doing something similar to a Rex property, which then gives you the memory information. But it will become super big once we start having literally hundreds of thousands of pages. Sean was next.
I was going to ask, so there's essentially two categories. You have memory that needs to persist, that is consumed by the entire system, so isn't tied to a specific VM. And then you have a ton of memory that's tied to a specific VM when you get into IO menu, page tables, and all that stuff. For the stuff that's not tied to a specific VM, what's the ballpark size of how much data you're expecting?
So the mechanism we have today has close to no global data. There is a bit. There's a bit of PCI data. There's a bit of
IMMU root page tables. That's not
no
VM.
Well, sure, okay. But
the root or not?
The root is not. Yeah. So there's also some IOMU metadata. What are the actual groups? What are the group IDs? All of that is also more global than VM specific. There's a bit, but it's not going to be hundreds of megabytes.
Yeah, it's a few megabytes, like PCI cache, let's say dozen megabytes kind of order.
Okay, so it's more than a few K, but less than
exactly
a few hundred megs.
Yeah. As we move more and more stuff.
Okay, so where I was going with this question is when we're talking about probing, so disclaimer, I know nothing about PCI probing and how the data is stored. Is that something where you actually do need to deserialize, serialize and deserialize, which is going to essentially establish an ABI between kernels?
Correct.
Or can you have, is it feasible to have something that sits outside of the kernel but has APIs with, it's kind of API, but not as restrictive, and you persist not just data, but also code for managing those things? Or is that just complete crazy?
Yeah, API is a problem, right? If you have to maintain that translated.
Yeah.
One of the useful ways of looking at this is as an optimization, right? It is ABI between one version of a given kernel driver and the next instantiation of itself. Nobody else cares. And the new version can look at that and say, actually, screw you, I don't trust you, or I have made changes, I don't want that, and just go and reprobe the hardware, right? In many cases, for the random drivers, the trivial example is loops per jiffy, right? Yes, you can do that on command line as well, right? But you provide a mechanism to pass blobs of data from one subsystem, one driver, to the next instantiation of itself, and that's private to it. So we don't have to think of it quite as much as an ABI as we do, a user space ABI, right? And many of those, it's just an optimization. Obviously, there are some things we really care about, like the page tables that have to keep working if DMA is still happening. There are things that aren't just an optimization, but thankfully page tables are kind of already an ABI anyway. So yeah, there are cases where we have to treat it fully as ABI. You asked about the size of what's being passed over. Do we have numbers for Zen? Because we've done this for Zen, right? We're already passing over, and in that case, it's also all the guest pages are marked as persistent to free this and the boot allocator.
Yeah.
But do you do things like PCI cache in Zen? You don't do that, right?
That's COM0 that handles most of that.
I don't think we have numbers, but we kind of feel that it would be a few megabytes, right?
I can't remember. We'd have to look at that. But yeah, we've done the same handover for Zen and just serialized the state. We basically used the guest transparent live migration ABI, which was already an ABI for migration in Zen, and passed that from one Zen to the next.
We do have a downstream non-structured implementation of this. But we could probably extract numbers there too, but it's not. I don't think that's the deciding factor.
Kind of as David said, there's what we need to do, and then the optimization. So, for example, in the PCI case, we will need to have a reasonably solid ABI with a complete state of VFIO. because that's going to be all the pass-through devices. But it's pretty simple. There's not a whole lot in there. All the random devices that only exist in the host, we don't need to initially. Now, we might be able to speed up the transition by enabling those drivers to indeed leave breadcrumbs and avoid redetecting things and whatnot, but that becomes driver specific and become targeted optimizations. So we have some control on the ABI surface here. And yes, we do need to be careful because we can easily end up into a mess there. But
yeah. So what you're talking about is it's actually independent of whatever solution we use here for parsing state, right? It's like, okay, we have a channel. What does the data look like? And we do need to figure that out. But the other thing that I'm keen to have in this discussion is some of the points that I've got here. Well, exactly, what does the channel look like? Yeah, and things like, do we have a hard separation between ephemeral, non-ephemeral memory? What do the users, like, what do they need to do? Do they need to allocate persistent, where they're like, I know that this is a persistent page, or can they just allocate normally and then later say, oh, by the way, these are all persistent? Yeah, anyway, there were questions.
So, can you guys speak about the mechanism you're going to use for persisting that memory across KExec? Is it going to be somehow a new node being created, the nodes being created in the device tree? Is that the handoff mechanism?
It's a platform-specific mechanism. On x86, you would use setup data. On ARM, you would usually use the DT because ARM always passes DT anyways. That's the two I have implemented so far.
So
it's platform-specific.
Using device tree as a mechanism to pass this stuff.
I'm using the data format of device tree to pass it. I'm not using the thing that you would look at if you were looking at device trees usually, which is a lot of standardization rather than the data format, right?
So my question is, if I'm interested in integrity measurements to be sane across KExec.
Yes.
Would this mechanism of passing, at least we have concluded that we can't really, pass in a new device tree with nodes that didn't exist before.
So you're looking at passing arbitrary data from the old kernel to the new. That could be a measurement, but it could also be other things. So of course you can.
So the mechanism we have today is we pre-carve out memory in the device tree that we first have, and then we are taking memory off of that. And so yours is more dynamic in terms of being able to change that from boot to boot. That.
I don't get the question fully, but sure. I
To
mean,
keep
if
in
you look at
mind-
x86 IMA, for example, it really is just a piece of blob that you pass and use in setup data. And this is just a more structured way of doing setup data.
And it's something to keep in mind that when you talk about device tree, we need to differentiate the device tree as in on platforms that are DT based or have a device tree that is this kind of general top level thing that represents your machine versus device tree as a simple semi-structured key value store. And the ability to use that and device tree fragments, we may or may not be anchored into the device tree. In fact, on x86, the device tree doesn't exist. We can still use the fundamentals of the device tree format as a key value store to carry arbitrary piece of information and define which properties we're looking for and all of that. So we need to keep those different. And there is some areas where they regroup nicely. For example, on PCI, we already have well-defined format to represent PCI devices in the device tree. We have code that is currently living in ARC PowerPC and ARC Spark that we could move to generic code to resynthesize a PCI dev from a device tree fragment. Need some work, but there is pre-existing things. Those things aren't new, and there is pre-existing, well-defined way to represent some of those things we're after already using that format. That doesn't mean it has to be the system device tree, and it can just be fragments that are specific to PCI or whatnot. But
yes.
I'm just curious, is there any overlap with power management, hibernation, freeze, restore? Because, that's kind of similar. The semantics are different. You lose different state, and when you come back, you have different state, but it does build a hibernation image. So
yeah,
I'm just curious what people think
there are
about
two some fundamental differences, right?
Mm-hmm.
One is you are always guaranteed to have source and destination be the same. So you have an absolute identical structure format between both. And the second one is that hibernation and suspend don't actually just serialize anything. They just literally contain the image as is, and then just put it somewhere else and boot it back up again. Like suspend to RAM, for example, is pretty much a no-op when it comes to any memory contents. Right?
The other fundamental difference in hibernate is the hardware is not in the state you left it.
Say again?
But the other fundamental difference in hibernate is that the hardware is not in the state in which you left it. A lot of what we're doing here is passing over information about the hardware is in this state. You don't need to discover it. You don't need to reset it. You don't need to configure it. This is how I left it for you.
Yep.
That is not the case in hibernate.
Sorry, I'll pass it to you in a second. We're touching on an important point here, which is actually a bug in KExec, in my opinion, and has been forever, is KExec today will shut down, will call the shutdown callback of every driver, which is wrong. It always was wrong. The shutdown callback would potentially spin down disk, turn the hardware off, and things like this. Semantically, what we want is to tell the driver that to leave the device in a state so that another driver can pick it up. Typically, that's what unbind and bind tends to do. So I think we need to look at that, and it's probably the time to start fixing how KExec deal with devices.
But it's not the conversation. Wait a second. There's a lot of questions. Who of you wants to talk about the data format? He goes.
Just one comment briefly. So one thing that I would really like to do with this is do a DRTM relaunch to reassert confidence in the integrity of my system across that KExec boundary, and to be able to resume with additional confidence in my state now. As part of measuring what matters or what doesn't matter, I don't have the answer. I just have the problem statement, which is the data that I pass across. There are some things that are going to be stable, and there are some things that are not going to be stable, things that are more tightly coupled to guest state. And like if you're passing if you are pre-allocating, hey, I want this guest memory to live in this PMM region that I've statically allocated for it, that's one thing. If you are gathering pages from all over and doing whatever with them, that's less stable. The stability of data across that boundary matters for measurement.
Correct.
I don't know exactly, and also separation of, anyway, so that's something that I'm thinking about. I have to go dive way further into the details to figure out the appropriate way to handle that. But that is something, a relevant consideration for what you're passing around and how you might separate that or not.
My current thinking is to basically make sure that at least strive to, maybe we won't get it working, but strive to always make it backwards compatible, right? Not forward, but at least backwards compatible, so that newer versions of the kernel can always read older versions of this transfer protocol, up to a point where we're basically saying, look, this is unsustainable, and then we just do a swipe and basically new version, and just we'll remove any backwards compat from the beginning, and then start from scratch, right? Just a couple major versions. No, like fully altogether, just like screw the whole thing, right? It's probably the easiest way to get this going, because I'm actually pretty sure we will be able to get backwards compat well done with a device tree primitive, because it actually ingrains a lot of exactly this, right? A lot of this notion of I have a versioned device node, I have a versioned field that I can then go and access. And as long as we don't multiply that information by 10 just because we happen to copy it through everything property, we can probably get backwards compat for pretty cheap.
Okay, and then for measurement, I guess I would write some expression of what paths in my device tree matter for what I...
Correct.
Okay,
Correct. Your measurement piece would literally just on boot say, hey, I'm looking at these previous measurements and check whether everything is still there, seat yourself from it, the same way you already do any IMA pass over on x86. Yeah. Just throw it. Just throw it. Throw it to whoever. Yes.
Thank you. I waited for a while. So first of all, I agree that device shutdown is not the right callback that we have. So I'm not sure if bind and bind is the right one. I know we had something like specific where we QS the devices disabling interrupts, which was what?
We don't want to query
Yes, but what I mean is that we could have something specific for KExec and default back to shutdown if that one is not implemented. But yeah, so I agree with that. Regarding the passing the data from one kernel to another, so one advantage that we have today with the emulated PMM when we can pass the at least the username data today, if we emulate part of the RAM, we can.
You mean with the mmap command line parameter?
So one of the advantages is that it actually can work with the going through firmware as well, in addition to going through kexec. And we have some examples where we actually go through firmware, both at my previous company and at the current company. And that means that theoretically it's possible to update the firmware as well during the pass. So this goes. This
I don't know if you want
into-
to.
What?
I don't know if you really want to. Like there are a
No,
lot
no.
of.
What I mean is that it's like today it's possible with the username. So if we had kernel state that is preserved on an emulated PMM device in whatever state, like in a separate pool, in like a regular DEX file system that is accessible by kernel allocator or some other way, it would be compatible.
We're not
with,
removing any of this. My basic thinking again is to completely separate these two problems for the start, right? So instead of you could still use a command line based PMM if you wanted to with any of this kernel passover and just continue to use a DEX file system for your user space memory backings. Nothing
no,
would
for
keep you
user
from
space,
doing
yes.
so.
But what I'm saying is that do not break it with the kernel as well. Allow it for the kernel.
Like if you want to keep your IMMU running.
You can't over a reboot because your firmware is going to reinitialize your devices. It's just not going to work.
It doesn't have to. The firmware can be taught to skip.
Look, if you have a private firmware that is doing special things that any normal reboot wouldn't do, then make it a special firmware call that you enable upstream to call as a
but
update
the problem
yourself
is
now
that
call.
with that special firmware would mean that that special firmware would have to skip special like ranges of memory. But with the emulated PMM, the firmware can be just told that this part of memory should not be reinitialized, this device should not be reinitialized, and so on.
I'm having a hard time wrapping my head around how you would keep the IOMU active over a reboot of the firmware. It just like semantically, I don't see how. Like you have to go either you have to go through power cycle for reasons.
You don't have to think about the IOMMU specific case, but what I'm saying is that if there are other reasons to preserve kernel data across the reboot, perhaps allow it by simply giving the interface to reboot the kernel from one kernel to another using this separate pool. That's what I'm saying.
That one is there. So again, current proposal of what I have, and I'm going to send an RFC soon, is literally a pointer to a DT formatted thing in memory that you may as well serialize out before you reboot, and you may as well populate. Don't over-index on the expense of serialize.
So I think if the first step, at least for here, is to like make a list of different tests, because we have seen that there are many different steps. Like Ben mentioned, shutdown,
yes,
serialization of file descriptors is one, serialization, and like the one that Ben mentioned about shutdown, it's actually the same as kind of skipping the device setup on the next kexec. Well, it's a superset, like.
Yeah, maybe.
Yeah, it's a new callback that can optionally serialize stuff. So another part is like figure out like the protocol to pass the serialized data, which can include pieces of user space data when you get into IOMMU, VFIO, whatever, but it can just be kernel data to begin with for the sake of getting the device drivers up quickly. Like yesterday, there was the other kexec talk mentioned ACPI, and there's no reason to run ACPI after kexec. So I guess at least we have two tasks. One is the serialization part, and there the prior art is cryo and all that kind of stuff, and there's something to be inspired about, except that you want to keep as many kernel data structures as possible. And the other is the kexec revamp. So I think these two are different things, if everybody agrees.
Yeah, and you don't want to make it
no,
ABI.
kernel data structures are not ABI, but IOMMU page tables get pretty close.
I had a question about PCONFS, the slide that you had before.
Say again, a question about?
PCONFS.
Yes.
So the first one, the IMME group one, I'm guessing that's an FS DAX.
Sorry, are you guessing it?
IMME group one, right? That's an FS DAX.
All I was trying to show here is the IMMU driver can put its page tables in this file system and refer to them by a file system path, right? So this would not be FSDAX. This is a different file system called PCONFS built on top of reserved memory. This is one of the proposals.
Okay.
You take your full system memory and you make most of it owned by PCONFS, not owned by the buddy allocator. And then user space can reach into there through file system paths, kernel modules and devices can reach into there through file system paths, and anything, you've got like a clean and hard separation between preserved persistent memory and non-persistent memory.
Okay.
There's a question online quickly before that. Jumping back to the structs are not ABI, totally agree on that front, but I think you do need to at least call out that you don't want to limit this to just like hardware enumeration. Because like, I mean, the loops for Jiffy, which is just comical, but it's an example of you want to be able to, it's very important to call out that you want arbitrary data passing and that you don't want to just restrict yourself to other stuff.
Yeah, and these were some other things that we thought. There was this, again, we kind of had this conversation a bit yesterday about KVM replay state, where you can get your VMs running super early if you define like what's necessary to set up a VM, and that's stuff that's entirely internal to KVM, basically, and pass that across. Yeah.
And then the question from the chat was, how do you manage fragmentation for ephemeral memory? Compaction would make things complex.
I think that is one of the challenges exactly with the serialization, deserialization here. You see, I did list that as the complexity of fragmentation. Yeah, Alex, maybe you can take that.
So the way we've done this in Zen is you have a boot mem allocator and you make sure you've got enough contiguous memory for boot mem. And only after you move from boot mem into the real buddy allocator, and all you're doing there is freeing the pages that are still free. At that point, you have passed the live update stream to work out which pages you can't free. And it works out quite well, right? That you have, as long as you have enough memory for your boot mem to get to the point where you're priming the real buddy allocator, at that point, you've done enough work to pass the stream and know which pages you can't use.
But in theory, your persistent memory can be fragmented all over the system, right?
Yeah, and in the Zen case, as I said, that includes the actual guest pages as well, which it may or may not in the KVM case.
Does anybody have a strong opinion on what the fundamental base layer should be? I think that's the main thing I want to take out of this conference. We can, as you said before, we can stack differently, right? We can have a file system as fundamental primitive and then stack metadata files on top. That also can have blob data on top. Or we can stack a metadata passover thing underneath, like the UI tree thing, and then incarnate maybe even a file system or anything else that allows you to propagate blobs overneath. I'm like, what I'm not able to wrap my head around yet is what is a sensible foundation that we then build on top of?
I think the answer is going to be it depends. Because I'm not joking, when you get to things like page tables, they're 4K aligned, they're massive, they're going to cover a lot of state. You're not going to want to serialize that. It's nonsensical. You want to pass that over verbatim. SMP state, you're going to pass that verbatim. What you care about is that this page stays there. It's persistent at this exact physical address. For things like device driver stuff, you could serialize to a restricted, bounded chunk of memory, and you don't have to persist a specific physical address. So I think that distinction is going to make the answer, it depends.
The man in the back's had his hand up for a long time.
This might not address quite the use case, but could we just do it all in user space with something like Creu, and drivers would add like necessary hooks for Creu to save their state, and then just do it all in user space and restore it again?
Yeah, if this was L4, maybe. It's a kind of comical answer, but like for real, the kernel only is allowed to trust the kernel for kernel metadata. If you were able to, if you would give random user space access to arbitrary pages, especially at the end of the boot of whatever your shutdown sequence is or anything, you're completely breaking any layering we have in Linux.
But I mean, it would be like specific apps saving off their state, you know, like if I'm using the NIC or
You have
GPU or
those too.
something, and
No, you have that's a completely separate problem from what we are trying to solve right now. So Creo still exists. Creo should exist. Creo is an amazing approach to save user space, application state. What we're trying to save is kernel
but if
state.
you've saved all user space, what do you care about the kernel?
I don't yet care about saving user space. I want to actually
Okay.
destroy all user space and recreate it.
Okay. Yeah, okay.
Yeah.
Actually, I don't think you want to destroy user space, because if you want to
I do.
preserve, well, yes, but if you want to preserve VFIO,
Yes.
that only makes sense if there is somebody on the other side
Yes.
of KExec that
I want to
puts-
recreate them.
Yeah.
But I want to. Okay.
Yeah, but I mean, you have basically
How much overtime are we?
Huh?
How much overtime are we?
No, you are not.
I got 4 minutes?
Yeah, you're
awesome.
not.
Super simple answer. The whole approach or the whole point of live update in the way we use live update in EC2 is to replace kernel, VMM, libc, everything across that update within less than a second, but ideally within less than 100 milliseconds.
Yes, so you don't have the checkpoint and restoring user space,
Correct.
but you still have user space itself,
Correct.
checkpointing itself,
Correct.
and restoring itself from
Exactly.
the other.
Correct.
So this is where the overlap begins and ends. Like it's done by the user space itself instead of being done by Creo.
Yes.
User space must be cooperative.
Yeah, exactly. User
Yeah.
space. So the point is, this is also why that I think it's good to separate the two things, because one thing is done just as a KExec optimization, just. The other thing is user space that requests from the kernel something specific, such as keeping VFIO running or keeping KVM running. And this is something else that the kernel serializes into his thing, because user space has asked to do so, right?
Correct.
Yeah, ask a question of like what fundamental thing are we willing to build. For me, like pkernfs kind of could supersede what we're doing with device stacks. Like I would love to find another use, like an additional use case for pkernfs to say like, okay, we don't need device stacks anymore because pkernfs can take over these use cases. One of the things that comes to mind is like CXL is going to have the concept of serial memory sharing between hosts, like one, and so serially sharing memory with yourself from one instance to the next is another concept. And so yeah, that's why I never engaged in pkernfs. I'm like, oh, it's kind of replacing things. It only has this one use case. I don't like until it tackles more use cases. That's why I'm not engaging on it. But
Actually, I have a question about device DAX. How can this replace it? Because as my understanding is, with device DAX, we have some metadata right in the device, right, to recognize that this is a DAX device, and then use that to restore the device after the reboot. Or like what like how exactly do you see that, like to replace it?
I mean, I just see this as yet another memory allocator. Like we have huge TLBFS, we have device stacks, now we have pkernfs. Like it's just like
it's got some key differences. So firstly, it's
they all
able
do,
to
right?
be used by it's able to be used by kernel code itself. Like IOMMUs can come and allocate from it, and it's on top of reserved memory. But I think that's the same for.
Yes. Yeah, and this is why I think it has dovetails with CXL, because like we have people in the talking about John Groves here's talking about shared memory between hosts, and he's like, oh, I want to build a file system for that, and we want to allocate memory, and like it's this kind of similar-ish problems that we're trying to solve, and trying to like how can we expand what we have and not keep creating another memory allocator.
But they're only looking at sharing memory between user space, right?
No, I mean it's sharing between hosts.
As a file system in a way, right?
As a file system.
It's still like the semantic is a file system, like a traditional file system where user space would access files.
Right. Yeah.
The novel thing and the very different thing about pkernfs is that the kernel is the user, and the kernel actually uses it as a base primitive to get a handle of allocations that no longer are anonymous at this point.
Right. I mean, but that's also useful. Like that we like right now we have a choice between you get an entire pre-allocated device and you can online the whole thing as user memory,
but people want this thing in the middle where they want the kernel to get pieces of this thing and use the
Okay.
allocator. So,
I
yeah.
see. Interesting.
Use it for it.
Let's talk about that.
Pose criteria to analyze possible solutions for the format in which you pass stuff over. Looking at it from a language theoretic security perspective, the grammar, the complexity class of the grammar that you express this format in has bearing on how safely you can write a parser for it. And if we want to reassert confidence in the integrity of the system afterwards, the safety of the parser that has to introspect the potentially compromised data from before matters a lot. So that is the way that I would, when I'm looking at whether I'm looking at device tree or pkernfs or like various internal potential representations that pkernfs might use, that is the perspective that I would analyze those things from.
Device tree is pretty well established on that one. Memory bound in a single location. That's good. How much time do we have until Nicholas?
Plus one, but you can go ahead for
I mean,
last question then.
Device tree is, no, what's kind of following up on this, device tree is just, again, an arbitrary key value pair. The problem is what you happen to put in there. And the definition of that is all over the place. And potentially, that's where we need to have some, potentially some formalism if we want to be careful and measurable.
I don't know quite why it matters, because the whole point about the measurement is that it's a chain and you trust what is running and then you measure what it loads and you have to trust that, right? And if the existing kernel that was trusted, yeah, and so
correct.
So checking the data that's passing over is pointless unless you're also going to validate that it has left the CPUs in a sane state. And one of those secondary CPUs that's supposed to be stopped isn't currently running and corrupting stuff in memory. I don't understand why it helps to measure what one kernel passes from the next, given that you have to trust the whole of the rest of the state of the machine that it left behind.
That's why I want to do an air relaunch if you mean for that case.
Yes, you're absolutely correct. That's why I think it's important to be able to do a DRTM relaunch as part of that KEXEC.
Final note, because I got Steve over to get into this room, and I would at least get that into attention. The current RFC I will send is going to implement ftrace handover, so that instead of doing all of this use case, which is the vision and the thing we actually need, we will first start with putting ftrace data from the old kernel to the new kernel, so you can continue ftracing all the way across KEXEC. The main intention behind that is it's a lot easier to reason about data passed through of KEXEC than reasoning about safety of passing through arbitrary IOU data and understanding what handle to use to actually reconstruct the data afterwards. We have a lot of problems. To make that problem set smaller, we will only concentrate at first on passing data as well as metadata. So if you're interested and curious about that, by all means, get in touch, and then we'll work with Steve to get that in.
There will be issues.
Okay, hello everyone. My name is Nicholas. I'm a kernel engineer at AWS, and all this work I'm presenting, but all these we're discussing, I've been doing with my colleague Anel. We already talked about our approach to doing VSM with KVM on the KVM from 2023, and sent a first RFC a couple of days ago. And the aim of this session is to maybe narrow down the abstractions to use to implement VSM. So let me set the stage. I'll talk 1 minute or two, and then we can discuss. We have two approaches that have surfaced. The first one was representing each VTL a CPU might have as a separate vCPU. And then for the things that are, among others, memory protections that are for the whole VM, we add VTL awareness to that. This introduces VTL awareness in the kernel. It adds some extra churn in the memory slot handling and memory management aspects of KVM. But it also adds some flexibility because we have VTL awareness in the kernel, so we can optimize some stuff. User space kernel responsibilities are not clear, and yeah. Sean proposed a couple of days ago that we implement a full struct KVM per VTL, which would contain also, which contain the VTL vCPUs as well as all the state that is shared by the whole VM. This has very nice things, among others, that all the memory management aspect of the VTLs comes for free. We don't have to introduce any VTL awareness. It's even nicer than that because there's no VTL awareness in the kernel. We might discuss whether that is good or not. From some perspectives, it is. The responsibility split is super clear, and yeah, it introduces a lot of complexity in user space because now we have to struct KVMs for a single actual VM. And yeah, I did some research there, and the QEMU aspects of that are going to be very complex. So this brings some feedback and some questions I'm posing the room and would like to discuss. First of all, in an effort to simplify memory management, are we introducing a lot of complexity into user space? Is it worth it? I wonder. Not having VTL awareness in the kernel seems like a good thing, but maybe it's not the right approach. Being able to optimize things in kernel with VTL awareness might eventually show up as a necessity. We have to agree on what constitutes a vCPU event for a poll interface. And can we discuss enhancements to the memory slot I/O control so that other users like Zon might use? For example, I was thinking of first-class overlay support. And yeah, jokingly, our memory slot address space is really that bad. Anyway, so this is VSM. And yep, I'm open for comments on my questions, if anyone has.
So Nicholas, what is the main motivation to kick all VTL awareness out of the kernel? Is it just to keep the kernel simpler, or are there nasty things that you actually have to do to make VTLs work?
There are nasty things that you actually have to do. One of the subtly simple things, if you have VTL awareness, you have to have separate EPT tables for every VTL. And so then you have to either have KVM restrict how many VTLs you can create, because if you have, I guess, the TLFS allows 16 VTLs. If you have to track 16 VTLs, the number of possible page tables you can create explodes, and you have to, when it starts to interact with other things that may or may not be in play for VSM, but are in play for KVM's ABI, then you have to worry about how the size of your counters to be able to track how many different page tables are possibly referencing a given page and things like that. So there's nastiness there. The memory attributes won't work because those need to be per VTL, which is currently per KVM. So we would take on complexity in KVM to allow per VTL memory attributes. And that's where you start adding everything up and you want the APIC isolation per VTL. Then you are adding VTL awareness to that. And you just get to a point, and same thing with mem slots. So you get to a point where you have 90% of your stuff is VTL aware per KVM. And it's like, okay, you're just eating memory overhead from a KVM perspective for that extra 10%. And you're complicating user space.
So unless they're going to be coming up with a new kernel, smaller kernel, that's going to run in the higher VTL level, what are we trying to solve here? If you're going to trust this kernel that's running there, which is the same kernel that's going to be running in a lower VTL level, see, in the case of Hyper-V, we got a different kernel that runs in the higher VTL on the Windows side.
This is not running Windows. This is for Windows. This is just the
That's right. What I'm saying is, in the case of the traditional Windows stack, when we run something else in a higher trust level, we actually have a different kernel that runs there as opposed to what's running in the main stack, right? So we do all credential guard and this other guards in a very controlled small kernel, right? If I'm going to be running the same kernel in both places, some of the advantages of this architecture kind of.
Both sides. Only host. This is both sides.
And my second point is, given that the newer hardware now, both SMP and TDX, are going to be having a notion of privilege level in hardware, right? You can actually achieve this by running, in 7SMP case, you could run this thing in a higher privilege level, potentially.
And it's transparent to the enterprise, so you don't treat it.
You should be asking these guys why they want to do this. From the to the point of TDX and SMP, those require special hardware. They have ABI that is defined by hardware vendors. Anything we can do in software, I'm 100% supportive of doing, because at some point, I mean, Intel's already deprecated TDX 1.0. At some point, they're going to deprecate 1.5, and then we've lost backwards compatibility, and we have a mess to deal with.
At some level, right, you could really think of this as a sidecar VM. KVM structure. So talking about really is just a second VM that's running a trusted stack.
Yeah, from a KVM perspective, and that's why I like the struct KVM approach, the least amount of awareness we have in KVM, the more composable KVM is to support other use cases beyond VSM. And that's why from like a KVM maintenance perspective, I'm not too concerned if we have a few hundred lines of Hyper-V specific code to allow user space to support VSM, but the rest of the changes in KVM are minimal, then I don't see why we wouldn't support it. There's not very many downsides.
So why do we want that? VSM in general? Because customers want to use it. Yes. And it's becoming a standard for the American government. So you have to have it. Slower. Yeah.
So for the user space side, and maybe this is a question for Paulo, how complex is it if we push most of this out to user space?
I don't know because I've never written the code. I know what I know is that at least QEMU doesn't really care that there is one or two VMFDs. It only has one because there was never a need for two. But for example, there was a case in the past where we wanted to have a second VMFD for SCV live migration helpers when they were a thing. I mean, it's a bit weird that you have to start two threads instead of one if you have two VTLs. But it's not really a blocker. Again, then it's also a bit a new thing that you have to poll in order to know when you become runnable and kick out of the run loop the lower VTL. There is some synchronization involved, some handoffs involved of the CPU state. Nothing is a particular blocker except possibly performance. Like how many times does Windows at boot jump into VTL1? Because like you're going to look at microseconds. Like just getting out of KVM into QEMU is like 3,000, 4,000 clock cycles with all the mitigations disabled. So Then you have to do the octals to get and set the CPU registers and so on, because they are copied on the hypercalls from VTL0 to VTL1. You have probably some kind of putX wake and wake up the other CPU. Like, there is overhead. That also depends on whether you can have one thread for running the VTLs, whatever they are, and one thread for waking up all the VTLs. Like, one thread can handle all the interrupts, and you can run the vCPU only in one thread that picks the right file descriptor. I'm making it up now, so I'm not sure. But
that would break a lot of core QMU, the run loop. It have to be worked out a lot, but it could be done. And
yeah,
especially
it's an implementation question.
Yeah. During boot, it happens a lot, thousands of VTL changes. During runtime, not so much.
Forget what is preserved across a VTL change in terms of CPU state. Like, are GPRs preserved?
I have a list here. Let me see. There you have it.
Okay, so FPU state, GPRs are the two.
We need a KVM get MSRs to do all that stuff. KVM get SREGs,
I just want to understand this a bit, this difference a bit better. So basically, if you do two different struct KVMs, it means there's no possible way to optimize the transition, the switches between VTLs. And you have to, every time you switch, you have to go and read all of those registers out from the one and write them into the other one. And there's no way to actually share state. Is that the main difference?
There's not no way to do it. There's no way to do it currently in KVM. But there's no way to do it currently in KVM anyways, because you would still have to, the difference would be if you have VTL awareness in KVM, KVM would be hard-coded to transfer that state as part of the VTL transition, and KVM would be affecting the VTL transition. Versus if you have separate struct KVMs, we would need UAPI of some form to allow a fast transfer of state.
And would that be a possibility?
For sure. I think if we went that route.
If we prove that user space is too slow?
It's a fairly low bar. I mean, anything that allows, the allure for me of primitives that KVM provides as opposed to a bunch of VTL awareness is that when some new use case comes along that wants to do something clever, I don't know if VM introspection might have had some touch points in here where they're doing crazy things with your trusted VM and your not trusted VM. Would we have gotten close to that, and could we enable them in some sane way as opposed to their 104 PAP series that they post every other year?
Okay. I have more questions myself, but maybe someone. No? Okay. So with regards to polling, go.
I was just thinking about the copying regs. I mean, the current proposal, the current prototype you've got, it still does use user space for copying the registers, right? You pull, because you have a separate KVM vCPU, not a separate KVM, but a separate vCPU for each VTL.
Yes.
And you still manually pull the registers all the way up to user space and put them back into the other vCPU.
Synchronize all the state upwards and then downwards.
We could talk about a model where you have an IOPTL which takes the other vCPU file descriptor and copy it. Sorry?
Oh man, that was a bad throw. All right. Super simple. Like at first, for this disclaimer, I think this is premature optimization. We shouldn't be even talking about this because the current implementation we have is doing everything to the nominal octals, and again on the other side, everything to nominal octals, and it still is blazingly fast. So I don't think we even have to worry about any of this. But if we wanted to worry about it, and I think it's a really nice thought exercise, I think we should implement run regs on x86, implement a get many reg ioctal that allows you to get, that gives you a list of one reg descriptors, and that way you just basically serialize a dynamic list of registers on one side, deserialize on the other side, and then we also solve all of the, QEMU needs to call the syscall 500 times just in order to synchronize state from KVM to user space problem throughout the whole ecosystem of KVM. See? Done.
Thank you, Alex.
I actually have a patch set, a branch somewhere, a private branch somewhere, where I implemented ManyReg, and the only reason I never sent it was because I never had performance issues with OneReg. So I was measuring, I was trying to accelerate our own hypervisor a bit, and it just didn't accelerate.
So we have 10 minutes for this that is probably the more complicated part. So
I was going to say, I think the long range people wound up building that as well in their first RFC for the architectural support too. But I was going to say, so are you still facing an issue with like needing a better like granularity for like controlling the guest physical address space? Like, I think that there's a very clear answer for handling the 2-struct KVMs, but like there seems to be a common use case for giving user space sub mem slot control over like more granular control over what the guest sees between the integrity stuff that we heard earlier and then this as well.
That we largely have solutions for that are per KVM, which is why I just want to say go use struct KVM, because we have per page memory attributes, which we have line of sight to do and read, write, execute permissions on. I mean, we have any number of bits per page. It's just a matter of how performance and memory heavy we want to make it. And then we also have, if you have per KVM, you have per mem slots, and you can do whatever the hell you want with overlay pages.
Giving user space the ability to control that as well, right?
Yes, that's there.
Okay. All right.
Because it doesn't solve it for the Zenguest use case. Zenguests often will want to just overlay one page somewhere, which currently involves taking away the larger mem slot and then putting back the bits both sides and the pages being overlaid. But it's also really awful and buggy. We've literally spent quite a long time trying to make it work, and it's complicated and awful to pause all the vCPUs and interrupt delivery because we can't just overlay a page on the mem slots. And so the overlays would be one way of solving it for VSM. It would be a very nice way of solving it for Zenguest as well.
A lot of that complication would be in the kernel anyway, because you would have to like not pause the vCPUs, but you would have to ensure that the EPT, like you remove one EPT, you put it back. Yeah, like I think it's not like nobody likes mem slots there, fair enough. But if you really think that it is a problem, just add like mem slots with different priorities. But it's not a huge deal to have it in user space. Like it's not a fast path, like Alex was saying. The memory attributes work for this case. They work for the hypervisor kernel integrity as well. Yeah, okay. I don't know how bad it would be to have multiple priority mem slots, but
No, that's priority. Yeah, multiple mem slots. Instead of the new one, there's switch. That's the priority.
That's a priority. Yeah.
So,
but I think
can we
don't have much time.
Use
so
a
let's
minute or
move
two
this
to
because
discuss
this is
the
important,
polling
yeah.
aspect. So essentially, it's what should we consider an event source for waking up a poll? Some thread that's waiting on poll on a vCPU. The way I modeled it myself was anytime a vCPU is kicked, the polling thread gets woken up. And I was talking with the Xon people. They proposed moving a vCPU that's waiting in user space into halted state and then monitor the halted state, empty state. And whenever we need to access, whenever we need to inject an interrupt, empty state will change into runnable, and then we wake up and going.
I would stay away from empty state because you also have guest state that's stored in empty state, and it's going to matter for other use cases, and we're going to complicate that a little bit. The guest goes into halt, empty state has to be halt because there are stupid guests that rely on being halted and like we've seen cases where the guest will unmap its code that it's executing from, and it relies on staying in halt. So if you have a spurious wake up, it'll blow up the guest. So that I would just stay away from. But like letting user space communicate its intentions with the vCPU, which is what you're talking about with MP state, is valuable for other things. Live migration blackout as an added defense mechanism when user space is stopping running vCPUs. At that point, you should say, I don't intend to run this anymore. If you ever try to dirty memory from this vCPU or emulate something for this vCPU, like die or kick out or something. So I think there's more use cases than just this for user space communicating a vCPU is paused or wants to pull or something like that. Just stay away from MP state.
Okay, fair enough.
As also there's a previous talk about multi-KVM, right? Like it looks like this, VSM seems to be another, kernel could be another hypervisor. I mean, wondering if these two topics can be aligned together. I mean, so it does not necessarily have to be two structured KVM. The other side, the other, VM for that, it might be drastically simpler. I mean, that might, the only thing that it accepts is that it has to be a common resource, code. Yeah.
It would be more complex because when you have two separate KVM modules, they don't have awareness of each other and they don't know the internals. And so it's harder to make them talk. Where if it's a single KVM module, KVM knows that if it gets a pointer and it can verify that it's the right type of file descriptor pointing at the right type of struct KVM, then it knows that the internal layout and it can directly poke into things. You can send IPs across VMs. You can say, I want to switch. Like I can imagine something where we got to, if we need to enlighten KVM to allow quick switches between VTLs, you have a hard binding between VMs and you have to have the exact same number of vCPUs and you have exact ways to go switch to that vCPU in this different VM. If you have separate modules, you have separate text, separate data, separate layouts, it becomes much more harder because to do that transition, you have to have well-defined ABI because you want to be able to have those be different, and then you have to have common touch points, so your complexity goes pretty high.
Right, but that's from a implementation point of view, like the code changes to the KVM by small, but you need to define yourself ABI.
I think Paulo's about to hit me.
Yeah.
Thank you very much.
Yeah. Yeah, we have 1 minute.
Oh, was it that or was it the box? Was it that or was it the box?
Yeah. Okay. Hello, everyone. Sorry, I know I'm the one keeping you all from lunch, and yeah, we're all quite hungry, so. So yeah, thank you very much all for coming. My name is Fuad, and I work on the Android systems team. I'm based in London, Google, and I work mainly on PKVM. And today what I would like to talk to you about is the work that we've been doing in terms of supporting what is now finally called guest memory for PKVM. So first of all, there's a lot of background information, and this is a lightning talk, so I don't really have time to go over all the background information. So I put here some pointers for you all to refer to later in terms of looking at in terms of KVM. If you want to only look at one thing, I strongly recommend Quentin's talk from LPC last year, where he goes into the details of PKVM, and as well pointers to the source code of PKVM, as well as the guest memory port. That one was done for version 13. So version 14 doesn't really have that many differences, so it should be pretty much the same. And there's another presentation in terms of the future use cases for PKVM. So there is just one thing I want to go over in terms of background, which is very important for understanding PKVM. It's the ARMv8 exception model. I think you've probably seen this before. This is sort of like a simplified diagram of what it looks like for Android and how we use it in PKVM. So in ARM, you have different exception levels. You have from EL0 to EL3. I'm only showing up to EL2 here because EL3 doesn't really matter. It goes from least privileged to most privileged. So EL0, you have your user space stuff. EL1, you have your kernel. And EL2, you have your hypervisor. And in terms of PKVM, you could kind of argue that all PKVM is doing is maintaining the stage 2 page tables in order to protect the guest memory. I mean, of course, it does a little bit more than that, but that's really its most important task is the stage 2 guest tables. And then you have the host kernel and some other PKVM stuff running in the host kernel that's maintaining its stage 1 page tables as well. And then you have the VMM as well as the virtual machine. So in terms of that, what are the similarities? Why are we interested in guest memory in terms of PKVM? So PKVM, similar to TDX, for example, it's confidential computing. I'm not going to go into details of exactly what that is. But the idea here that we have is that the host, the way that we carve out memory for the guest, which is also similar to TDX, is that the host needs to donate the memory to the guest. And what we're doing for PKVM, after the memory donation happens, we need to make sure that the memory doesn't disappear, doesn't go anywhere. So at the stage 2, the hypervisor makes sure that it's protected. But in terms of EL1 or the host kernel space, we really need to make sure that the memory is still there somewhere and it's not going away. And for that, we're currently using in PKVM a long-term gov, which isn't really ideal. And as well, what we're currently doing for PKVM is that this donation happens from just your normal anonymous memory. So the host or user space allocates anonymous memory in the mem slot, user space address, and then that gets donated to the guest. Now, the problem with that is if this memory can be mapped by the host. Currently, we don't really have any way to prevent the host or a user space process running at the host from mapping that memory. And what happens if that happens, what could be a problem is if a user space process tries to access that memory, then at least this is slightly better than what would happen, for example, in x86. We wouldn't get a machine check. We would just get a seg fault to the user space process. So that's not really that bad, because if the user space process wants to shoot itself in the foot by accessing memory that it can't access because it's being protected by the hypervisor at stage 2, that's fine. And here, because the host kernel knows where to deliver the signal to, it knows that, yes, this user space process accesses memory, so that's the one that I need to deliver the signal to. However, the problem is that it is possible that a misbehaving user space process could trick the host kernel into accessing that memory. So for example, by doing strace or somehow getting strace in the host kernel to access the memory that's being, that's mapped, of course, the hypervisor at EL2 will catch that access, will send the signal back to the host, but the host kernel doesn't really know what to do with that signal, so the whole thing will crash. So still, confidentiality of the guest is maintained, but the problem is that, yeah, well, the system is down now.
Anything that does get to the pages.
Yeah, exactly. And The lack of a good solution for this has been the biggest obstacle for us in terms of upstreaming PKVM. And one thing I need to point out about PKVM is that it is actually running. It is in production code. It's been in Android 13 since, or in Android since Android 13, which is 2022. So it has been around, and we've upstreamed quite a bit of it, but there is still quite a bit more to do. So for us, when we saw the work that's being done on guest memory, we thought that, wow, this is really a great fit for us. We would like to adapt and use it. But here's the key. There are some differences in PKVM, or actually there's really one major difference in PKVM, is that the protection, like I mentioned earlier, it happens at stage 2, and it's really simply the way that we protect memory is stage 2 protections. Either it's owned by the guest, or owned by the host, or shared by the guest. And there's, of course, different variations, but that's it. It's really just about toggling protection. There is no encryption. Memory is not encrypted. So this is software only. And the reason why this difference is kind of important is this gives us an opportunity in PKVM, which is a little bit more difficult in stuff like, for example, TDX or ARM CCA, is that we could share memory in place. And if sharing memory in place means that memory can go from being, no, TDX, you have to bounce it back and forth. You have to use a bounce buffer to copy it back and forth.
You change the page. You mean as you change the page from shared to encrypted, you have to recopy the content?
Yeah, exactly. Yeah. In PKVM, we don't have to do that.
You can't in TDX. You literally can't in TDX. Once your VM is running in TDX, if you insert a page into the guest, which is what happens because you can't do in-place conversions, the only data you can insert in the guest is zeros. So, but the other side of this is we're talking, some of the use cases are like hundreds of megs. And so any kind of copying is a non-starter. And so the in-place conversions, which means just sharing without being destructive to the data, is the key use case.
Okay, I was just going to observe, we didn't really think of that when we did the SVSM. It does a lot of in-place conversions because AMD can do it.
So let's jump forward and like see what are the user space API implications and what we want to talk about.
Yeah, so the main use case that was actually do that is DRM. So when you're talking about DRM, you're dealing, I know, with 4K frames. That's going to be a lot of memory, and that memory, it would be a huge overhead to copy it back and forth when you want to do the conversion to bounce it. Keep in mind that we're running this on a mobile phone with very limited memory, and we're always struggling with getting enough memory on a mobile phone. So that's really the biggest use case for us, and that's really the biggest difference in terms of requirement for PKVM as opposed to the original idea, or which guest memory was envisioned for. So yeah, to go to the problem statement, in other words, all we really need to be able to do in PKVM is to be able to mmap memory. But if we just mmap memory, then we're back to square one, where you're mapping memory and you're risking that memory is going to be accessed when it's not, when you're not allowed to access it. So we don't want to just to mmap memory, but we want to make sure that we can only map memory that is owned or shared with the host, and memory that is private to the guest cannot be mapped. So this is really the key difference or the additional requirement that we want with for guest memory. And this is
the kernel itself knows whether it's the memory is currently shared or not. When you have the exact
no, actually that's one of the problems. One of the problems that the kernel, at least for us right now, or until guest memory came along, the kernel does not know whether the memory is shared or not. There is no tracking the kernel. So as you see here, EL2s, the hypervisor knows whether memory is shared or not. EL1, the host kernel, the host kernel doesn't know whether memory is shared or not. So this is one of the challenges, actually.
It has to in order to make that decision.
No, it doesn't. That's the point.
I understand, but the way it works in SMP, for example, is to make a request to say this page now should be shared. That EL1 in your case would always know about. I mean, I don't.
Sorry, no, I was going to say the difference here. SMP runs at EL2, not EL1 in KVM. That's the difference.
Conceptually, it's the same. EL2 here is basically what your SMP firmware would be, and then you have the rest. Same difference.
No, conceptually it is the same, but the thing is, this guy over here, the host kernel, can't or currently doesn't have access to what's happening with the stage 2 page table. It doesn't know it. It cannot currently know.
But it could get a notification, right? It
Yeah,
could,
yeah. I'm not saying
like
that
PKVM could tell it using either
exactly,
a bitmap or using a proactive event.
Yeah,
interface
exactly.
or
Yeah. I agree.
whatever.
Yeah.
Or you could always have
Yes.
your stage 1 thing, your host kernel, be the one that acts permission changes in PKVM, right? So it always would be a handshake between the two.
Exactly.
And only
You're kind of stealing my presentation or what I'm trying
So I
to
think get to the next slide. I think the problem statement, and like we're running low on time, get to what we need to add and what the difficulties are, because you're spot on. The problem is, how do we safely transition between it's shared, and then how do we get it back to not shared and not have dingling?
Exactly. Yeah. So exactly, this is the point. So the idea is that we need to maintain state at EL1 to track that. Yeah. And this has been really the biggest challenge. And the idea, or actually maintaining the state is pretty easy, but really just making sure that we don't have any race conditions, that's becoming that is the tricky part. So the idea is that we have essentially, we could say that we have 3 states we care about here for a page. So this is what I guess frame looks like really. I should have had the text a little bit bigger. I apologize if you can't read, if you're having a hard time reading this. But the idea, each frame conceptually has 3 states that we really care about. We have what the kernel, as in the EL1 sees, what the kernel thinks about, well, what it is, what the stage at what the sharing state at stage 2 is, which is whether it's shared or private, and whether it's mapped. So one of the changes that we did was using the new attributes array, added so that attributes array tracks, by the way, whether user space thinks it's shared or private. But the whole idea is that we can't trust user space. We can't trust user space letting us know, hey, it's private. So what we did is that we added another attribute to the attribute array that doesn't really track whether it's shared or private. It just tracks whether it's mappable or not mappable by the host. And this attribute can only be set by the kernel. It cannot be set by user space. So, and the way that this attribute gets updated is on exits, on every kernel exit. So when the guest shares memory with the host, we had the KVM exits that was there already. We didn't add that. But when you exit to the host, you exit to the host for the reason for the exit. And you have a page that has been shared with you. And then the host sees whether it's shared. It can clear the flag, whether it's mappable. Or by the way, the flag is no map because it maps with private. So because no map and private, ideally, anything that's marked as private should be marked as no map. And anything that's shared should be mappable. So but it doesn't really matter. The polarity can be inverse, but we just thought that it made sense for it to be set when it's private or not. But anyway, and we're using the exits whenever we exit in order to set that or to clear that. And the invariant that we want is that we never, ever want to have memory being mapped and at the same time private for the guest. So this is really the invariant that we're trying to prevent here. So the biggest differences really, or the changes that we've done was, first of all, support map and fault. And then adding these states and making sure that on every transition, so this is the state space, only one of these states can change in every single transition to make sure as well to avoid races. And in terms of going from every state to the other, making sure that to allow that transition to happen, making sure that if it's something that is shared, then it cannot be mapped. And the idea is that in PKVM, everything is private by default. And going from private to shared isn't really all that scary, because here you don't really worry too much about potential races or anything, because here if something becomes shared and you just, there's a little bit of lag in terms of allowing it to be mapped or not, it's not a problem. The problem is going the other way around. The problem when the guest has shared something with the host and then it tries to revoke the sharing again or make it private again. And this is where we really need to be careful to not have end up in any state where anything is mapped by the host and having that mapped by the guest. And here, one of the tricky parts as well that the current solution that we have is, how do we deal with a guest trying to unshare something that is currently mapped by the host? What do we do? So first, when the host gets the unshare request, we check whether it is mapped by the host or not. And if it's not mapped by the host, that's not a problem. But if it's mapped by the host, then we wait for that, or we exit to the host and give it the opportunity to do one of two things. First of all, to either unmap it, and the second part, which is to acknowledge that it's private or not. So how does the host acknowledge that it's private? By using the attribute array and saying, yes, it's actually private now. And if the host has acknowledged that it's private, and at the same time it hasn't unmapped it, then we consider it to be an error behavior on the host. So we exit back to the host saying, no, there's an error here, an error condition. You said that it is private, but you haven't unmapped all references. But the host as well can, let me just finish the sentence. The host as well can decide that, no, I reject the unsharing. I want to keep it as private, in which case the hypercall that the guest has issued to unshare it will get the denied or the negative act saying, nope, the unshare did not succeed.
So you want to keep it as shared, not as private.
Yeah.
Okay. So basically what you're adding here is a notification mechanism between the hypercall to EL2 that makes the guest, the host validate the transition.
Yeah, exactly.
Okay. So, and what happens in, like, how do you know if it's, so one step back. The mappable is a guest virtual address, right?
Yeah, GFM.
Sorry, guest physical address.
Yeah.
And the other one is also guest physical address.
Yeah, they're both
but
guest
from
physical
the point
address.
of view of the stage 2.
Exactly.
Process. So how does the host know that it is mapped?
We check the map count.
Okay.
You also have the inverse, that if that shared memory was given back to the host and then the guest wants it back as private, you have a protocol to ask the EL2 and then accept that memory as coming back into the confidential guest.
So this is, so you mean when the guest wants to reclaim it as private?
Yeah.
Yeah, exactly. This is what happens, but the host needs to acknowledge as well.
Right.
Because one thing is, which we don't support yet, but in the future, there's a problem of multi-sharing. So for example, the host could have shared it with a third party, for example, Trustzone or something like that. And then the host could simply be not able to revoke the sharing. The host could be, or the host, some other entity other than the VMM for some reason has mapped it, and the VMM cannot unmap it. So
regarding just a quick question on have you run into problems in testing of things other than your VMM having maps that have caused especially spurious failures because something else in the system was tracing or doing something funky and just happened to grab a reference at the wrong time?
I haven't run into it, but the thing is, to be completely honest, for the time being, we don't actually have any use cases that do an unshare. So currently, all the use cases that we have only share memory, they never unshare. So all the tests that I had to do for unshare were use cases that I just created for testing because we don't have any actual existing use case that's unsharing.
That makes a lot of sense. Well, you may have this patched on the list from someone, forgot who, to do dynamic software TLB sizing. Right, so you can dynamically expand and shrink your bounce buffer region, and there unshare is actually pretty useful. You mostly care about reads, not writes faulting, right?
Care about both, really. It doesn't really matter for us whether it could be read or write. I mean, it's the same, really. Any access doesn't really matter. We don't really care about one more than the other.
Okay. So I was just thinking, like, what if you could have a force unmap that literally just remaps to a 0 page and ignores writes in a way, right? And then you just basically steal that memory from the host.
Yeah, that would open a can of worms, I think.
Yeah, so they considered that for, I think in the context of the SMP series that was proposed along the ideas of, on an RP violation page fault, instead of just killing stuff, you can just map it to some other page. But there are lots of examples where there's a lot of code where if you hit it and you're blindly doing that, what if you're wrong and you're suddenly overwriting kernel text? Because of some other, like you take one bug and then you make it far worse by doing something that you shouldn't be doing.
Reference to something that then in the kernel goes.
Yeah. And we're out of time.
Okay, thank you very much, everyone.
Thank you.